So welcome to the Energy Frontier session, and it is a pleasure that we are welcoming the first speaker, who is Giacinto Piequadio, who's going to tell us everything we need to know about the latest result about the Higgs measurements.
Good morning, everybody. So I'm very excited to be here to present you the latest on Higgs boson measurements from ATLAS and CMS. And clearly we'll do so on behalf of the two collaborations. So let's start from the global picture. So the Higgs boson was discovered in 2012, and this opened the way to the exploration of a whole new sector of the Standard Model Lagrangian. This point was made also yesterday, which is responsible for the electroweak symmetry breaking. So there are two types of three-level couplings, so the Standard Model particles, which then determine all the phenomenology, all the Higgs production and decay modes. So there's one term which is the coupling to bosons, which arises through imposing gauge invariance, and the other which is a different and sort of ad hoc term which represents the the coupling to fermions. And I will insist quite a bit on this in the course of the talk. What's the legacy from run 1? I'd like to start there to have a clear reference. So the Higgs boson mass was measured to a precision of 0.2%. This is important, not only because this is one of the parameters of the Standard Model, but also because it fixes the Standard Model predictions. On the second point, the Higgs boson couplings were measured to 10 to 25% precision, as this plots with the results on the constraints of the coupling modifiers from a global fit to the ATLAS and CMS data shows, with very nice agreement with the Standard Model. And Higgs to invisible was constrained at the level of 25 to 30%. There were first studies on spin, CB eigenstate, differential distribution. They all were compatible with the Standard Model within the uncertainties. Is this good enough? And the answer is immediately no. So first of all, the coupling to fermions were not fully established yet in run 1, especially the coupling to top and bottom quarks. In addition, one can use general EFT arguments or look at some specific beyond the Standard Model at the scale of a TV. There are not many new studies, but this one SOMAS shows that the deviations on the coupling modifier were expected are in basically all cases below 10%. So the precision that we have achieved is not just enough yet to probe some of these models. In addition, the BSM effects may be enhanced at high transverse momentum. Naively, that's where you access smaller spatial scales. As you can see, for example, in this distribution of PD of the Higgs boson, depicting very different BSM scenarios. And it's actually great progress. So in this talk, I will show some of the highlights from both the ATLAS and CMS based on the analysis of 36 or even 80 inverse femtovar of run 2 data, which corresponds to either till 2015 or 2016. And this is already up to 3 times the run 1 luminosity. And the results, like from last month, presented at ACP, are already sort of old. So I quote as new results that were released for ICHIP. So in addition to the increased data set up to a factor of 3, what also helps is the increase in center of mass energy. And you see here increased by a factor of 2 in gluon fusion, up to a factor of 4 in associated production with 2 tops. And this helps to have many millions of Higgs bosons produced in the ATLAS and the CMS detectors, part of which we can then collect and analyze. Starting from the purest Higgs boson decay modes, so ZZ and diphoton, these have low branching ratio, but they are very pure. They have high mass resolution. They allow mass and precise differential measurements. I'd like to start from there and highlight the progress on the measurement first of the mass. So here, new measurements have been presented by ATLAS, Higgs to diphoton, Higgs to ZZ, and CMS. Here, the precision in the end for run 2 CMS ZZ alone, which is 1.7 per mil precision, from ATLAS to the combination 2.1 per mil. And this is already better or similar to the full ATLAS plus CMS run 1 combination. And I should stress that this result is still limited by statistical uncertainties, so it will improve further once we collect more luminosity. Another important parameter is the Higgs boson width. So this is about 4 MeV in the Standard Model. It's too small to be directly accessed. The only model-independent limit we can set is at the level, the best limit is from CMS, is from Higgs to 4 leptons. It's at the level of 1 GeV. But with some model-dependent assumptions, you can also measure this decay width through the ratio of the on-shell to off-shell cross-section. You can see this here, since the on-shell cross-section is virtually proportional to the decay width, the off-shell not. If you assume that there's no new physics which enters in the production and decay modes when going from the on-shell to the off-shell scale, then you can build the ratio and determine a limit on the width. So Atlas has a new run-to analysis with Higgs to CC to 4 lepton and 12 to nu. You see the 4 lepton distribution in this plot for masses above 220 GeV. And the limit you can get is here. So it's now at the level of 3 to 4 times the standard model prediction, which is up to around a factor of 2 better than both the Run 1 Atlas and CMS expected limits. The theory improvement here was, the theory treatment here was improved significantly. And this is thanks to new theory computations that were made available. These channels are also used for precise differential measurements. So what I've depicted here on the left is Higgs to diphoton. And on the right, the combination of Higgs to diphoton ZZ and actually even Higgs to BB bar from CMS. You can see now that you start to be able to determine even the high PT Higgs relation with not too bad precision. This is unprecedented. There's good agreement with the predictions. And as you can see, there's no sign of new physics in the PT Higgs tail. In addition, there were several other distributions, many other differential distributions that have been measured. There are several new results, and all distributions are in agreement with the expectations so far. One of the highlights of this talk will be the progress on the coupling to fermions. So you can indirectly probe this, and we already did this with the discovery of the Higgs boson, through the gluon fusion loop and through the loop diagrams in the Higgs to diphoton channel. However, in order to distinguish possible new physics contribution entering these loops, and instead the 3-level coupling, you really want to access this directly, measuring the fermion couplings in the Higgs decays to leptons, dyne-type quarks, and in the TTH-associated production mode. And I will highlight this one by one and highlight what is the progress on this. So I will actually start from my favorite one, so Higgs to BB bar. So here, in addition to probing the coupling to B quarks, one should be reminded that the branching ratio to BB bar represents the largest in the standard model, so it constrains the total decay width and so the measurement of absolute couplings under mild model assumptions. It also drives the indirect limit on undetected invisible decays. The previous results here are the evidence by CDF and D0 in 2012, and in 2017, the quite convincing evidence by both Atlas and CMS at the level of 4 sigma. So I'm very glad to be able to present today results on Higgs to BB bar by Atlas. The results by CMS are just in preparation. The VH production is the most sensitive to decay mode for Higgs to BB bar at the LHC, which is otherwise killed by the overwhelming multi-B-jet background. There are 3 channels depending on the decay mode of the W or Z boson. What we do is we select high PT W or Z plus 2 p-type jets in the event, and the main discriminating variable is the invariant mass of the B quark jets. You can see this very nicely in this plot, which now includes 8 inverse femtobarn of data. There's a sig Higgs peak that you have to disentangle from large non-resonant backgrounds, TD bar single top, W plus jet, and Z plus jets. The overall strategy here is to take normalization from data that's poorly predicted and the shapes from the Monte Carlos. And so there's really a lot of work which went into getting more reliable predictions. For example, we use NLO matching using Sherpa. Then we use the invariant mass distribution of PTV and the angular separation of the 2 bits to train a BDT with a few other variables. We then fit with this BDT across different categories. And we summarize the fit results in terms of the bins of the BDT shown as a function of log S over B. And you see on the left the data and the prediction from basically the background, and it aligns very well. On the very right, you see an excess, which is this red thing, which is above the expectation from the background. And this is and this gives rise to a clear signal, which is well modeled by our simulation if you insert a signal strength of around 1. So this excess amounts to significance of around 4.9 sigma, slightly less is expected. If we add run 1 data, which has a slightly lower low signal strength, we get at around 5 sigma expected and observed. So this analysis is difficult. As said, there are very large backgrounds, no resonant, which are not challenging to understand. So we do several validations. So first, we fit the dye boson signal, where instead of looking for Higgs to BB bar, 125 GeV, you look for Z to BB bar at 90 GeV. And and you retrain the BDT for that. You look at the results. The signal strength is compatible with the standard model with a significance of now remarkable 10 sigma. In addition, what we also do, if one doesn't trust the boosted decision tree and MVA technique fully, instead we do apply a fit to the invariant mass distribution of the two B quark jets, and we get again a results compatible with the standard model, but with a lower significance, which is what you would expect. If you project this fit result on the invariant mass of the two B quark jets, summing up over all categories, and subtracting the non-resonant backgrounds, what you see is a clear emergence of Z2 BB bar peak, and on the right shoulder, there's the emergence of the Higgs BB bar at the level here of around 3 to 4 sigma. So this all validates very well the analysis. We also did something more. We combined this with other production modes looking for Higgs BB bar, and we get well above a 5 sigma observed and expected. And also we combine with other channels looking for the VH associated production, and again we get more than 5 sigma. So this is the first observation for Higgs BB bar, and similarly, first observation of VH production. Coming to the coupling to tau, so Higgs to tau tau, here what we do is we try to address all possible decay modes of the taus. Hadronic reconstruction of taus is pretty challenging. We have categories that target vector boson fusion production and gluon fusion in the so-called boosted regime. The main discriminant variable, similarly to the B quark case, is the invariant mass of the two taus. It's more challenging because you have the missing momentum from the neutrinos, but this is crucial to distinguish Higgs tau tau, which is a pretty small peak, on top of the large Z2 tau tau background, which you then have to control really very well to extract a Higgs tau tau signal. The results of the fit is shown on the left, and on the right, CMS and Atlas over a different number of categories. The result, as you can see, there's a clear emergence of a peak in the ratio at least, and this is enough to claim clear observation of Higgs tau tau by each experiment alone. You can also appreciate that the signal strength, so what we see in terms of sigma divided by the standard model prediction, is well compatible with the standard model prediction within the uncertainties. Coming to the coupling to muons, so this is a very suppressed decay mode in the standard model, so it's very difficult to probe, but now with the increased amount of data we have, we start to be able to access it. We just look at events with two opposite sign muons, and then we categorize such event based on variables which give you an idea of the expected invariant mass resolution of the two muons. And a boosted decision tree is an MVA technique which enhances the VBF contribution, as you can appreciate in this left plot from CMS, where you can see on the right of this distribution there's a small sort of an enhancement of the vector boson fusion contribution. Still pretty small with respect to the backgrounds, given the rate decay. Then this is used to define some categories. We apply in each of these categories a fit to the invariant mass distribution, very similar to Higgs 2 diphoton. And we extract the background in a fully data-driven way from the sidebands using analytic functions. And the results are depicted here in terms of limits. The limits are at the level of twice the standard model, so we're getting pretty close. This is for each experiment alone. Here CMS profits from the better muon resolution. Atlas has already integrated more data. I would say by the end of run 2, we should be really, really close. Let's come to the coupling to up-type quarks. So this can only be probed in the associated production of Higgs with two tops, given how heavy the top is. It's particularly interesting because it's the largest, the quark with the largest mass and the particle with the largest mass in the standard model, so it's very sensitive to the emergence of new physics. Here, it's a production mode, so we can access it over a variety of decay modes, from the purest one for lepton and diphoton to the one which are less pure but have a higher signal yield, like Higgs to BB bar. And we have both Atlas and CMS have analyzed all these channels. So here's the new Atlas results with 8 inverse femto, where you start to see the emergence of a clear peak on top of a much reduced background, which is due to the fact that you're requiring additional activity in the event to target TTH production. The multi-lepton channel, WW tau tau, and the Higgs BB bar decay modes are more challenging, and therefore what we use boosted decision trees in both cases. And we estimate with quite some care the backgrounds, which are especially difficult in TTH due to the uncertainty on the TT bar BB bar prediction. And you can see the significances here. Once you combine them all, you get a signal strength which is compatible with the standard model expectation. with an error of around 25 to 30%. And in both cases, the significance with respect to the standard model only predictions, it's at the level of more than 5 sigma, which is enough to claim also observation of TTH production. Let me come briefly to single top plus Higgs. This is a new CMS result. In principle, the standard model expectation for this production mode is very suppressed. But if you would happen to have the opposite sign of the coupling to top and the vector boson than in the standard model, then you will see an enhancement by almost a factor of 10, and we will be sensitive already with the present data set. So CMS has two analyses which target explicitly TH production in Higgs to multilepton and Higgs to BB bar. And this has been now combined with a reinterpretation of the TTH Higgs to diphoton, the two TTH categories. And the combinations is used to make basically a Likert scan as a function of the top coupling, as imposing the vector boson coupling to B1. And the idea here is basically to compare the one here, which would be standard model sign, relative sign, up and KV, and opposite sign. And you can see that you expect to this favor opposite sign by 4 sigma. What you see is a bit less, 1.5 sigma, to the small excess in Higgs to diphoton. Nevertheless, this is complementary to constraint for Higgs to diphoton and ZH production. Let me go ahead. So combining all Higgs boson measurements. So there's a lot of work done by both Atlas and CMS to combine all these measurements. Here CMS combines a few more modes, a combination of production and decay modes, and Higgs invisible. Atlas already integrates a little bit more data. You can see the results of the combination in terms to fit to various different production modes separately. Gluon fusion and the others, and here on the right. So a few observations. So first of all, on gluon, the measurements of gluon fusion, we get now to a precision of 9 to 11%, and the result is compatible with standard model. This is closing up, especially once we will combine, on the state-of-the-art theory prediction, which has around 5% uncertainty. In addition, here on the bottom right, as an example, I've shown the significance with respect to the background-only expectation of Atlas plus CMS run 1, and Atlas as an example of single experiment. And in all cases now, all main production modes have been observed. Some results in terms of couplings. So here on the left, there's a plot of the couplings as a function of the particle mass, and you can see there's a very good agreement of the several orders of magnitudes of masses. On the right, there's a result by us on the ratio of couplings. This is the only thing which we can really measure at least in a model-independent way. There's the coupling on the various particles and effective coupling from the top and the diphoton loop. As you can see, the ratio of couplings are all compatible with the standard model, quite remarkably, with precision of 7 to 10% for vector boson to 17 to 20% for B quarks, and we expect this to improve very soon with the 18-verse femtobarn data set. And this is already better than the run 1 Atlas plus CMS combination. A slightly auxiliary topic, so measuring Higgs invisible decays. This is quite interesting because it tells you whether there's something missing in the branching ratio that we haven't seen. So here, in order to see Higgs invisible, you have to exploit a recoil from another system, and the most sensitive production mode is vector boson fusion. In CMS, this study was now done for run 2, and it was combined then with the associated production and gluon fusion. The most sensitive is vector boson fusion. The limit is at the level of 24% in branching ratio to invisible, while 18 is expected. You can also combine this with the indirect discrimination from the global fit, which I shown at the previous slide, and you get to an expectation of now 16%, which is quite remarkable compared to previous results. So let me come to the last topic of this presentation. So there's still another parameter of the standard model Lagrange that we would like to access, and it's basically the parameter lambda, which determines the Higgs part of the Higgs potential, the trilinear and the quartic coupling of it. This is very difficult to access. You can access it, as you see, through di-X production, which has a destructive interference between two diagrams, one with single and one with double Higgs production. The cross-section is much smaller than single Higgs production, at the level of less than 1/1000 of it. On the good side, you have many possible decay modes since you have two Higgses, which now can be explored. And Atlas and CMS started to explore quite a few of these. And I'll show the results on this slide, which summarizes them. Especially, these are the limits on the left for Atlas in terms of multiple of the standard model prediction, observed and expected. And the same here for CMS. And the new results for iChip that I want to highlight to you are BB tau tau, which has significantly improved sensitivity with respect to previous results. It's a level of 13 times the standard model, 15 expected. And the CMS4B results, and very remarkable, the combination of all these channels. And this has now an expectation of excluding 13 times the standard model and a bit less in terms of observed limit. So we are getting close here, in both cases, to 10 times the standard model for the Higgs production. And here the goal is relatively long-term, is to reach standard model sensitivity by the end of high luminate LC, but already start preparing this, also in case there is some significant enhancement due to beyond the standard model contributions. CMS moved forward with the results, also interpreting it directly in terms of a constraint on the three linear couplings on the parameter lambda. Here, there's a scan on the limits on the cross-section as a function of this parameter. You can see that the limit changes a little bit with the three linear coupling, which is due to changes in the acceptance, due to changes in the spectrum as a function of this parameter. In red, there is the prediction from the standard model in terms of cross-section as a function of this trilinear coupling. And you can read the limits where there is the intersection between the observed limit on the cross-section and the predictions for the cross-section. And the expected one is, let's say, at the level of minus 10 to 10. The observed one is a little bit worse. But this is sort of the status that we see for run 2, nicely depicted in this plot. So let me conclude. Thanks to the first 36 to 18 inverse femto-bond of run 2 data, the bosonic decay channels entered an area of precision measurements, as you've seen with some of the differential measurements. We have time 3 improvement in precision with respect to run 1, and this is without a combination of the experiments that is still ahead of us. We have direct observation achieved for all production and decay modes, which is now nicely depicted here. We just sort of filled these gaps. We have direct confirmation of couplings to all third-generation fermions, so top quark, bottom quark, and taus. And as you've seen, the sensitivity to double Higgs production is now approaching 10 times the standard model. The Higgs, I hope I convinced you in this talk that the Higgs physics is an important indirect probe for new physics. Of course, I showed you that we also have seen no deviations so far from the standard model. At the same time, we are really still at the beginning of a long journey. We only analyzed less than 3% of the final LHC luminosity, so stay tuned for more updates in the future. Thank you.
Thank you for this comprehensive review of the recent results. Now the floor is open for a few questions. Yep, Dimitri.
At the beginning of your talk, you mentioned very clearly importance of precision measurements of the Higgs couplings. Yeah, but the recent, I would say, comprehensive predictions for the full high luminosity LHC data set was made quite a few years ago. So are you planning maybe for the coming European strategy to update this, because it's very important for comparison with all other proposed collider projects?
Yeah, I completely agree. I mean, so the reason why I haven't shown that, and I actually don't even have them in the backup, is that we are redoing those studies exactly for the European strategy meeting and in the final part of the year. So hopefully we'll have a full comprehensive set of results at that time.
Very impressive result. Some people, probably some of us, even 10 years ago, some doubted the existence of Higgs. It's incredible that we can measure all of these things. Now, in your page 16, you don't have to go there. There was, when you combine with run 1 and run 2, somehow your significance stayed the same.
Yeah.
Is that because there was I guess, a statistical fluctuations, or is it experimental systematic error changes? And what is that? And then also, just finally, if you comment on what is the area where you see that it's most sensitive to new physics, or is it just you have to look at comprehensive all places?
Yeah, so about the first question, the reason why the significance stays the same is that the signal strength that we measured in run 1 is about 0.5, although with a large error. So it's compatible with the results from run 2. However, if you combine them, and actually if you just weighted average, one can realize that the significance actually is such that it doesn't change. So you improve the expected, but due to the sort of most likely downward fluctuation, the significance stays the same. Instead, in terms of expected, of course, you see that the significance increases, and this is expected, especially the sum in quadrature of the significances, basically. In terms of the second question, so which is the sort of physics measurement that we are performing that is most sensitive to new physics, I think it's a little bit subjective. So I've actually shown at the beginning what are in some sense it's driven by prejudice. No? At the beginning, I've shown some of the ideas. So for sure, if you look at the high transverse momentum, it means that you are exploring smaller scales, even naively. So that's a good place to look for deviations. TTH production, the coupling to top quarks, is the largest in the standard model. There are many new physics scenarios that would change that first and in a more significant way. Higgs to BB bar is also interesting because it's the largest branching ratio. So if you see a deviation, you might see that there's a part of the branching ratio of the Higgs which goes to something else. So yeah, there are many places. So we really need a comprehensive set of measurements in order to try to address all these places.
Generally, we see very nice measurements by Atlas and CMS, and they tend to agree between the two very well, and it all looks pretty good. But here on the left is where I think we see pretty much the biggest discrepancy, where CMS's observation power is a little worse. Could you speak a little bit to why that is, and if we expect CMS to get a little better here?
So first of all, I wouldn't call it discrepancy, no? Because it's actually relatively good agreement between the expectation and the observation. What you are pointing out is the different sensitivity of the analysis. So there's one thing which I should immediately stress is that the Atlas analysis uses 8 inverse femtobarn of data. This doesn't explain the full difference. Clearly, it's a factor, let's say, square root of 2. There's another difference is that Atlas has re-optimized this channel for specifically this production mode, maybe more than CMS. Atlas uses 7 categories, CMS uses 2. So there I would expect most of the difference to be explained by differences in the analysis. I mean, you can see that, sometimes CMS does better, sometimes Atlas. For example, TTH, Higgs to BB, that's very sensitive to how you estimate the systematics, and there CMS expects more than Atlas, for example.
So we should maybe expect the CMS one to come up a bit.
I think they will naturally converge towards much closer numbers in the future, yes.
Thank you.
I don't see any other hands up, so let's thank the speaker again.
Thank
you. Now I invite Dr. Luis Skinari now to tell us all of the recent results about the top quark and electroweak measurements.
It's a great pleasure to be here today, and I will discuss recent results related to top quark and electroweak physics. So to start off, I just want to highlight that top quarks and electroweak measurements play essential roles in testing the standard model. And although the standard model has really been studied at colliders for decades, unexplored terrain still remains. And this involves what we're doing now, really confronting the model in challenging regimes that were previously inaccessible, looking at very high energy, very rare processes, etc. And these are very important input for tuning Monte Carlo generators and constraining PDFs. An initial important component in this is also that these measurements really help both constrain and potentially observe contributions due to new physics. And particularly sensitive are very rare production processes or processes that involve, that are sensitive to anomalous couplings. And in addition, top quark and electroweak processes are background to all direct searches for new physics, as well as for Higgs measurements. Many results have been shown during these days at ICHEP, and so in this talk I'm really focusing on the most recent results, so the full details refer to the detailed parallel sessions. So just to set the scale a little bit, this shows production cross-sections and a reminder of how that relates to the number of events and luminosity for different processes that we're looking at. So first, in the electroweak sector, we go from looking at single gauge bosons, dibosons, electroweak production of gauge bosons, and similarly in the top quark, from pair production of tops, single production of top quarks, and tops produced in association with other particles. And this also shows the, this shows also the corresponding number of events in the 2016 data set, and you can see this really ranges from very, very abundantly produced processes down to processes that are really rather rare. So to talk a little bit more about measurements in the electroweak sector, we can think of this in two components. So on one hand, we have production of single gauge bosons like WZ boson. These really provide very high statistic samples in order to extract standard model parameters and test the self-consistency of the standard model. For example, we look at very precise measurements of the W boson mass, here showing the LEP combination, Tevatron, and also a recent measurement from Atlas. We also look at the weak mixing angle. I'll come back to that. On the other hand, looking at production of multiple bosons, this is a very sensitive probe of gauge interactions beyond the standard model. These analyses typically go something like you try to measure very precisely the cross-section of the process. You probe potentially anomalous couplings, triple gauge couplings, quarter gauge couplings that are not either allowed in the standard model or are very rare. And we're also now starting to really study processes involving vector boson scattering, or VBS processes. So first, just to highlight a few recent results related to single bosons. I think this is very nice to see that not only are we looking now at cross-sections differentially or double differentially, but we're really starting to probe this triple differentially. This is one example from CMS looking at triple or up to triple differential photon plus jet production, which can have sensitivity to PDFs. Another example is from Atlas looking at triple differential cross-sections for Drell-Yan production. Here, in bins of dilepton mass, rapidity, and angular distribution. This can have sensitivity again to PDFs and also weak mixing angle. Similarly, also LHCb is looking at single gauge boson productions here with the recent results in forward production of Z boson decaying to tau-taus. This is observed as compatible with a prediction from the standard model, and also looking at lepton universality, comparing the decays to taus versus electrons and muons. One topic that has been discussed quite a lot during these days is measurements of the effective leptonic weak mixing angle. So the weak mixing angle is a key parameter in the standard model. Typically, this can be extracted by exploiting the forward-backward asymmetry in Drell-Yan events, either EE or mu-mu events. Typically, it involves something like fitting the mass dependence of the observed forward-backward asymmetry to standard model predictions for different values of the weak mixing angle. So this is what's done at the Tevatron, and we've seen a recent result from D0 in the dimuon channel. At CMS, we instead fit both the dilepton mass and rapidity dependence, which is shown here with a forward-backward asymmetry in bins of different dilepton rapidity and versus mass. So here it's shown for dielectrons. There's also a recent result from Atlas, which is extracting the weak mixing angle using angular coefficient in, again, different mass and rapidity bins. And what's interesting here is that this Atlas result also has enhanced sensitivity by including not just the central region, but including forward electrons, where these effects become more prominent and therefore enhances the sensitivity. So this shows the current state. We have the recent results from Tevatron, combining the addition of the mu channel for D0, the most precise single experiment from LEP and SLD, where there is a 3 sigma deviation, which is one of the motivations for why this is very interesting to pin down at the Tevatron and now at the LHC. We have the results from CMS at 8 TeV, which is shown here, along with the newly presented results from Atlas and ICHEP. And you can see, so this point is with just the central region and then including also forward electrons, which really help reduce the uncertainty here. And in general, I should say that for the LHC measurements, typically the dominant uncertainties are statistics and parton distribution functions. This is one example from CMS, looking at a projection from where we are now towards the high luminosity LHC upgrade in how these uncertainties can be further reduced. So partly you can see by going from central region, including higher seed rapidity, which is from the fill to the open points, you reduce the uncertainty quite a lot. And then in addition, by constraining the PDFs as part of the measurements, these uncertainties can really be pushed down a lot. Switching towards dibosons, looking at neutral bosons of Z or Z gamma, in particular, standard model ZZ production is an important background for Higgs to ZZ and also direct searches. And there are recent measurements here from both Atlas and CMS. So we both measure the standard model process, as shown here in just one example, looking at ZZ, the differential cross-section here versus number of jets. In general, see very good agreement between the data and predictions from different Monte Carlos. And then, in addition to doing that, we can also search for neutral triple gauge couplings, which are not allowed in the standard model. And these processes are sensitive to such couplings as shown here. And this just shows one example for the Z gamma analysis, which for the search, one looks at high PT photons. And again, here no deviations is observed, and so very stringent limit on these type of couplings can be placed. Also, when it comes to WZ, both Atlas and CMS have had recent results here at ICHEP, looking at inclusive and differential cross-section measurements in the fully leptonic final state. We see good agreement between data and prediction. As an example, I'm just showing here, for Atlas, a measurement of the ratio of the cross-section for W plus Z to W minus Z, comparing the different channel and the combined. An example from CMS looking at a differential cross-section versus the PT of the Z boson. Also for these, beyond measuring just the cross-section, Atlas is looking at measuring the polarization of the WZ using lepton angular distributions, shown here for the W with the longitudinal polarization on this axis, and then the transverse polarization here. And so you see the data and the predictions from two different, from Monte Carlo here. CMS interprets the WZ analysis or extends it to search for and place stringent limit on again, triple gauge couplings. Here you see the sensitive variable, which is the mass of the WZ pair, and these colored lines indicate the enhanced production due to various anomalous coupling. In addition, we've also seen a lot of results related to vector boson scattering processes. These are a key test of the electroweak symmetry baking, and again, can be sensitive to anomalous couplings, specifically quartic gauge couplings. And they can also be enhanced in beyond standard model scenarios, such as involving a modified Higgs sector, new resonance, etc. And so here, the characteristic signature, I should say, involves, you have the scattering process, but then two forward jets that have a large rapidity separation and a corresponding high dijet mass. And so that's what's shown here as a sensitive variable from CMS for the first observation in 2011. You see the excess of events compatible with the prediction here in orange, and similar now new at ICHEP, a similar observation from Atlas, looking at the dijet mass variable. Also for WZ, another vector boson scattering, or the vector boson scattering process, we have the same characteristic signature, which is forward jet. And new at ICHEP, Atlas is observing this process. You see here the sensitive variables using a BDT with an excess of events. CMS has a bit of an underfluctuation here, but this result is also new. And CMS is looking at interpreting this or going beyond and placing limits on triple gauge couplings and charged Higgs, placing very stringent limits on this process. We also can look at ZZ, which is an even rarer process for the vector boson scattering process, where you again have the forward jets and look at the in the tail of the mass of the dijet, where we don't quite have sensitivity yet, but we're approaching it, and so with increased data, this will be very interesting. All right, so switching from or toward the top quark sectors. So top quark measurements are interesting in a number of ways. First, just to point out that the top quark is the heaviest known elementary particle. It also has a lifetime, which is very short, meaning that it decays before hadronizing, and we can really observe the properties of the bare quark. And in many ways, it's a window to new physics, both through direct searches and indirect measurements. And this sketch just shows example of different physics processes that we can look at, such as looking at cross sections, the width of the top, flavor changing neutral currents, spin correlations, etc. First, looking at top quark pair production, which allows us to test precisely QCD predictions, extract some standard model parameters, as well as to constrain top quarks as a background process. And the inclusive TT-bar cross-section has really been measured now from at around 2 TeV at the Tevatron up to 13 TeV from the LHC. I just want to highlight the most recent addition here, which is a point at 5 TeV from the CMS collaboration. And then we have the recent results at 13 TeV shown here, which in general, we have good compatibility with the theory prediction at high order and perturbation theory. And I should also say that at 13 TeV, the most precise measurements are now approaching about 4% in uncertainty, where the dominant components is modeling and also actually luminosity, which is becoming important here. All right. In addition to being produced in pairs, top quarks can also be produced singly. The dominant channel at the LHC is the T channel. We also have the TW and the S channel, which so far has only been observed at the Tevatron. Typically, the extraction of these cross-sections rely on multivariate techniques in order to distinguish between the signal and the backgrounds. This shows an overview at the different center mass energies, 7, 8, and 13 TeV. And we have T channel, TW, and the S channel, for which we have no measurements at 13 TeV. To highlight one recent result from that was shown new at ICHEP, which is single top reduction in the T channel. And so here, CMS is doing a precise measurement of the inclusive cross-section and the ratio of the T and the anti-T. Overall, showing good agreement here. This is comparing to different PDF sets. The good agreement is observed here. Another thing involving single top is looking at single tops produced in association with another particle. We now have evidence for the production of a single top in association with the Z boson, both Atlas and CMS, showing the sensitive variable that is used here, and you see the excess of events in the tail. And similarly, also evidence for T gamma at CMS, showing in green here, and both in agreement with the standard model. I also want to point out that top quarks are really everywhere now, or as it was described in one of the sessions, the Tevatron particle. At LHCb, we're measuring forward top quark production, so looking at the high rapidity range in the LHCb acceptance. top quarks have also been observed in proton-lead collisions at CMS. I also want to say a few words about measuring tops differentially. There are really an abundance of different measurements versus different kinematic variables. These can help, again, test theory predictions and constrain standard model parameters. And one thing that I think we'll come back to in the next talk is looking at the differential cross-section versus PT of the top quark, where there is a mismodeling that has been seen for quite a while in the PT spectrum, which is improved but not solved by including higher-order electroweak corrections. Another thing I wanted to point out is that we're also starting to look, as I mentioned earlier, really in the high energy regime, going to the very boosted regime, where this is the result looking at the momentum of the TT bar pair, comparing to different next to leading order Monte Carlo generators. And new at ICHEP is also looking at top quark pairs produced different, or looking at them differentially when they're produced in association with B-jets. And so the modeling of TT bar plus Bs is particularly important for the TTH with H2BB measurement. It's actually the dominant uncertainty in these measurements, and so an improvement of the modeling will have a direct translation in improving those analyses. And so for this particular result, both inclusive and differential cross-sections are studied. This is showing the mass of the closest BB bar pair. There's some discrepancy observed, but in general, this will be very valuable input for tuning the Monte Carlos further. I also want to say a few words about top properties. So for the top mass, which is a key standard model parameter, we have a range of measurements, the Tevatron and at the LHC. This is, I just highlighted here first 13 TeV measurement, and also we have a new measurement in the all jets final state from CMS, measuring the mass at 172.34 GeV with a systematic uncertainty of 0.76. Another reasonably recent result is a combination of the final CDF and D0 results looking at the forward-backward asymmetry in TT bar events. And so this is something that the Tevatron is particularly sensitive to due to the PB bar as opposed to PP collisions. And so this is done using the rapidity difference and resulting asymmetry between the decay leptons. And so this is something that there have been a lot of interest in the past, where there have been discrepancies, but now with the recent result and very precise high-order calculations, the agreement is within 1.3 sigma, looking at the forward-backward asymmetry versus the mass of the TT bar pair. Another new result for ICHEP is looking at spin correlations. And so this is done at 13 TeV. And for top quarks, the spin properties are transferred to the decay leptons. And so here it's extracted from unfolded cross-section with respect to the difference in pseudorapidity between the leptons. And this shows the normalized cross-section versus the sensitive variable here, comparing the black points in data, and the green is the best fit result, with, in blue, predictions from the nominal TT bar Monte Carlos, which is the next to leading order in QCD, or in red without any spin correlations. And so here a discrepancy is observed with respect to the nominal sample, which is at 3, depending on how you account for the uncertainty, either with or without on the theory prediction, between 3.2 or 3.7 sigma. Another aspect of this is if you assume that the scale of new physics is significantly higher than that is probed in direct searches, one can constrain contributions due to new physics, or constrain new physics contributions due to higher order operators using EFTs. And so one recent example, which is looking at the same variables, so the phi variable here, using the differential cross-section to constrain top magnetic dipole moment. This shows the cross-sections, and the green is the standard model prediction and different values of this C to G operator, placing very stringent constraints. So coming back to this picture that I showed at the beginning, we have from the very abundantly produced towards the very rare. And so just to highlight down here for top production, which is very, very rare compared to TT bar production. This can be sensitive to new physics, new high mass scalars. It also has sensitivity to the top Yukawa coupling, as is shown by the analysis at CMS. And both ATLAS and CMS have results here, where ATLAS is seeing a 2.8 sigma above the background only hypotheses, driven by the same sign lepton channel. And in addition, I want to say also, going even further to the very rare flavor change in neutral currents, which are highly suppressed in the standard model. They're sort of on the order of 10 to the minus 15 down here. And a range of different analyses are targeting these. They're the blue and red points here. And the color bands show different beyond standard model predictions. And so we're just now starting to really become sensitive to these new physics contributions through these type of analyses. And just finally, I also want to point out that there's a lot of prospects for top and electroweak physics at future colliders. There are a range of different future lepton colliders being discussed, both linear and circular. Just a couple of examples with a proposed collider called CLIC that would really have be sensitive to top quarks in a whole new regime compared to what we have looked at before. And looking at the other linear colliders, we can really provide very high precision, for example, on the W mass, very improved measurements of the weak mixing angle, etc. So just to conclude, measurements in the top quark and electroweak sectors are really key in continued testing of the standard model and searching for physics beyond it. We've seen a number of new results presented here at ICHEP, such as really pinning down the weak mixing angle. We're on the road to doing detailed studies of vector boson scattering with the observation of both WW and WZ for the VBS process. Have a range of precise top results, including some discrepancies, and starting to probe the really very rare standard model processes and continuing to hunt for hints of new physics. And I also want to point out that the results that I showed here from the LHC are based on data that were collected up to year 2016. And so we really have significantly larger data sets on tape already and are expected through the end of round 2 and round 3. And then further on the horizon, both the high luminosity upgrade of the LHC along with proposed lepton colliders leads to a really great potential for continued top and electroweak explorations. Thanks.
Thank you, Louise, for this impressive amount of result which you managed to present in the limited time allocated. So we have time for a few questions. Professor Ward.
Good morning. Very nice talk. I wonder, could you, in general terms, say something? What sort of how much QCD itself is limiting sort of the precision of your results? And it's a bit of a general question, so I understand if it's difficult to answer, but maybe you could reflect a bit on it.
So maybe I can just make one comment, and I think in the next talk where we have the theory perspective, that might be more on that. But so I showed, for example, the modeling of the top PT spectrum, where we still have discrepancies, and we've had recent developments from the theory community, including electroweak corrections to these high-order calculations that help, but we do still have, we don't have a perfect description of our data in all parameter space for sure. So in some sense, things like that is something that we then have to account for in, for example, some of our searches if you know that there is mismodelings. So I don't know if that answers your question, but it might be also come back to some of that in the next talk.
Thank you. Thank you. Yeah.
My comment and question are sort of related to his question, but I'm looking on your spin correlation discrepancy that you showed, and I couldn't really tell what era you're at. You said it goes from 3.7 to 3.2, depending on whether you have
Yeah. So maybe
so
there was some
what era are you using for the theory?
So the 3.2 is, the difference here is if you include the uncertainty on the theory prediction. And so, I mean, it's the Pauheg Monte Carlo that this is looking at. But maybe I should say more generally here that this is brand new, this result, and I think input from the theory community is very much welcome here to understand further if there are effects related to the modeling or something else that are not accounted for.
Okay.
Yes.
So another related question. So this is from Atlas experiment.
Yeah.
So what would be the CMS perspective for this?
So I think probably the CMS perspective is this. So this is looking very much at the same type of distribution, but doing an interpretation in terms of effective field theory. CMS doesn't have a direct, exact corresponding interpretation of the measurement at 13 TeV. And as I said, this is very new, so yeah. But here you can see that it's the same type of cross-section, looking at the differential cross-section versus different in phi, and placing limits within an EF team framework on these couplings.
Okay, so we should wait.
Sorry?
So we should wait for their analysis, taking this data into account.
Well, I think in general, a lot of these are very new results, right? We need some time to really digest and compare and understand further.
I don't see any other hands up, so let's thank Dr. Skinnari. So we now hear about the theoretical side of things on electroweak and Higgs. From Dr. Dolan.
Thanks to the organizers for inviting me. Thanks to all of you for surviving the banquet and coming in this morning. So I get to follow on from these two lovely experimental talks and give you a little bit of theory, opinion, and perspective to sort of let you know what we've been doing, which is we haven't all been entirely idle, basically, in response to all these results. So this has been a really enjoyable ICHEP, in particular for top Higgs and electroweak physics. It's been outlined through the plenaries and parallel sessions. There's been a whole rake of new results and additions to old results. And theory, so basically sort of the message I'd like you to get today is that theory has been working hard to match the kind of experimental precision that we're now achieving. And some of this experimental precision, when you have these standard model measurements, then can feed back around again into new constraints on standard model parameters, but also on the existence of new physics. And then at the end, I want to say a little bit about some orthogonal development about resonance tagging with machine learning. So part of the message that, one of the 300 other people on the plane I was on from Melbourne had a cold, and now I also have that cold. So one of the sort of messages from this morning's plenaries has been the abundance of differential distributions. And I'd like to sort of emphasize that again in my talk and what we can extract from that from a theory perspective. So I'm going to sort of start with top physics. So as we've heard before, the top is really a pivotal part of our understanding of beyond the standard model and electroweak symmetry breaking. It has the largest coupling with the standard model Higgs, so it usually connects in some way with the hierarchy problem if you have a favorite solution to the hierarchy problem. And the top mass itself, the value as in this by now well-known plot, is connected with the metastability of the standard model vacuum, right? So the yellow region here shows where we have a metastable SM vacuum, and we're sort of perched quite intriguingly in this sort of funnel region on the edge here. And so whether we're stable or unstable depends very much on the precise value of the top mass. So it's interesting from that perspective. So obviously, it's not just the value of the top mass, but tops decay, and they give you neutrinos, and they give you B quarks, and they give you leptons, and all of these things are interesting from the perspective of beyond the standard model searches. So just as an example, so here's a CMS search for stops, right? So you can produce supersymmetric partners of top quarks. They'll decay into tops plus missing energy, and this gives you this whole array of the same final states I was talking about. And the backgrounds here you can see are totally dominated by top quark production and single top quark production, basically. So this is something we have to understand, not just because top quarks are great, but if we want to sort of find resonantly produced new physics, we have to understand these backgrounds. And so top quark physics at the LHC is now high precision physics, right? So this is a cross-section taken from the LHC top working group at 13 TeV, so that you can see the central value, this is next leading order, is about 830, 800 picobarns or so. So these are large cross-sections going up to nearly 1,000 if you get to 14 TeV. And tops, this means that tops are everywhere. As we heard in the previous talk, they're now, and in these parallels, top quarks are now popping up in LHCb, they're popping up in proton-lead collisions. So if you we have about, we heard yesterday, about 100 inverse femtobarns, just over 100 inverse femtobarns for each experiment. With these cross-sections, that gets you nearly 200 million TT bar pairs. If you push on to sort of the end of run 3, this means that towards the end of run 3 and beginning of Halloumi, the LHC is going to be gigatop, right? So we used to hear a lot about giga-Z. The LHC will be gigatop pretty soon, and we have to have the theory precision to match that if we want to exploit these measurements to the utmost. And that's sort of been a large focus of the community within the past few years, right? So if just looking at this slide on top physics, we now have, so the current state of the art is next leading order in QCD matched with next leading order electroweak, okay? So the rule of thumb basically is that alpha S squared, about 0.1 squared, is approximately the same as alpha, about 1 over 100. So if you're calculating next leading order in QCD, you should also be calculating next leading order in electroweak. So this has been done last year, and these next leading order electroweak effects are pretty important, right? So this is from the theory paper here. This is the PT of the top, and you can see down here, so this is the prediction, but this is the ratio here, basically. So this is the ratio of QCD plus electroweak, so just QCD. So if you include the electroweak, next leading order, you don't. And you see precisely in the tail out here, I mean, this is going out beyond what we have at the LHC at the moment. We're sort of around here at the moment. You see that these electroweak effects are they're softening the PT spectrum, right? And this is sort of exactly the kind of discrepancy that Louise was describing in the previous talk. So incorporating these effects is really important. So this impacts the tails. So the tails are pretty interesting because if you have boosted tops, these are interesting. So you want to be describing the tails pretty well. But once you're looking at boosted tops, the flip side of that in theory is you're introducing scale hierarchies. You end up with scale hierarchies of the PT of that top, which can be pretty large relative to the top mass. Once you have these scale hierarchies, you start have to worrying about doing resummation along with your fixed order calculation. So again, the current state of the art from earlier this year is next leading order in QCD plus an improved next to next leading log calculation, right? So this hasn't been matched with the electroweak yet. And there's been, again, work this year in calculating the two-loop soft function. Theorists are moving towards NNN, so next leading log resummation to describe these tails better. There's also been a lot of work. So these results are basically looking at 2 to 2, right? So PP to TT bar. We're also moving beyond, so the narrow width approximation basically, looking at off-shell production, incorporating decays. And there we're at NLO plus NLO electroweak off-shell. So it doesn't quite match this yet, but that's because this is 2 to 2. And once you're talking about incorporating decays in NLO, the top goes basically to a B quark and a W, and you incorporate that decay as well. So its top goes to BL nu. So this isn't 2 to 2, this is 2 to 6. So this NLO electroweak calculation is the calculation of a one-loop 8-point function, right? So these are incredible calculations. And that's where we are at the moment. So one thing you'll notice is we have sort of a lot of stuff. Here's one which is NLO plus NLO electroweak. We have some resummation which is separate from that. We have some off-shell stuff which is separate from that. There's a whole story of Parton, matching the Parton showers. And so one thing we're going to be doing, moving towards in the next few years, is integrating all these calculations into one place. So once you have this precision, you can do awesome measurements. You can extract alpha S, for instance, from the top cross-section, right? So this is just a measurement of the cross-section. This was done once the next leading order TT bar cross-section calculation has actually been done 5 years ago. I mean, not by CMS, but by Chakon and Mitov. And soon after that, CMS did a measurement of alpha S. There was another paper last year, which I want to talk about by these guys. So this is a combination of theorists like Gavin and Bethke and some experimentalists, Kleimer and Gunther de Sartori. So the world average on alpha S is 0.1181 plus minus 0011, and then by sort of varying alpha S, you can extract, so here's the measurement here on the left, of Atlas and CMS. You can extract a value of alpha S from top physics. And we heard as well, you can also use these same kind of precision calculations to extract sine theta W. So this paper here, which I just want to briefly talk about, these people have they've done something slightly different than CMS. So they've tried to take a more conservative approach, and they've used Bayesian statistics, which I think is nice. So you can take the top quark pole mass, that's an uncertainty, that's a central value, but there's some uncertainty on that. And then you can calculate your sort of predicted value of the sigma TT bar. And then you can stick that in as a prior, right? So the theory prediction is basically your prior. It has some central value. It depends on parameters like MT and alpha S. You then have a likelihood function. That's basically the measured experimental result. We're doing Bayesian stats. So you convolve, obviously, all the uncertainties in there. So then you multiply your prior times your likelihood. That gets you the posterior. And you integrate out. You marginalize over the parameters you're interested in. So this is in alpha S sigma TT bar space. So you can integrate out over the cross-section to get yourself a value of alpha S. The 68% confidence interval is here. And you get a number over here, right? So 0.1177 plus minus 003. So this is slightly larger than what CMS extracted. They've tried to be a bit more conservative in their treatments of uncertainties and whether they're using resummation or not. So things have moved on a bit since there. The point I wanted to make is this is just using a cross-section measurement, and you can improve on this once you include differential information. So another thing we can get once we have this differential information is constraints in the gluon PDF, as has been mentioned. Right, so we have fully differential distributions with stable tops, right? So this is not with decays yet. And this allows you to do next leading order PDF fits with top quark pair distributions. So this has been done by a few different collaborations now, right? So CMS have extracted it, Chakon and Nadal did it the first, and now this is sort of appearing within the NNPDF collaboration. So the nice thing about this is it gives you a large decrease in the uncertainty of your gluon PDF at large X. Right? So this is something that would be directly relevant, for instance, in BSM physics. So the 3 plus in the top here show the gluon, but also charm and B quark PDF. So the blue line is showing you sort of the decrease in the uncertainty at large X. This is the gluon luminosity function. And you can see, so the baseline is the green here. And once you put in differential top quark information, you get this large decrease in the uncertainty at large X. Okay, so what happens when we include this differential information? So NNPDF have gone and done a fit, and this is from earlier this year, and now they have differential information on top pairs, on Z transverse momentum, and inclusive jet production. So they can extract now an extraction of the strong coupling constant. The current world average is with this error. The result from NNPDF is basically with the same error now, so 0.1185 plus minus 1%. So once we have this sort of differential information, the extraction that we're getting from the PDFs, including differential QCD information, is competitive now with the world average. It's basically the same. And you can sort of think about further improvements from using boosted tops with this electroweak and resummation improvements, and looking towards particle level distributions as well. So there's a bright and interesting picture here. Awesome. Okay, so moving beyond once we have all these beautiful standard model constraints, you can feed that back in and try and sort of extract some BSM physics, right? So one of the reasons we're interested in these tails is from the perspective of beyond the standard model physics. And this is particularly another sort of, why you want to do differential information. So you might have a beautiful distribution like this, and we think, how can we find BSM physics? Well, you could look for sort of some bump. I mean, this one is the Z, but you can go and do a bump hunt if you're producing stuff on shell. But again, the information out here in the tail is pretty valuable. Is this thing dropping off, or is it rising up? And if it's rising up, you could be starting to resolve a Bright-Wigner peak out here that you can't produce directly at your collider that you have, but you're starting to see this rise here. So again, this is really precision BSM in some sense. So what do we have here? So I'm going to talk a little bit about top EFT and other EFT in that perspective. So the whole story with EFT is we have the standard model Lagrangian, and then to parameterize our ignorance in some sense of the effects that we don't know, we add in higher dimensional operators, right? So there's one dimension 5 operator you can add in, so it goes straight to 6 here and then to 8. The dimension 5 operator is only one, it's the Weinberg operator, which gets you neutrino masses. And then it's known now that there's 59 of these operators you can write down at dimension 6. You can write down some at dimension 7, but they all violate lepton number or baryon number. And then there's more at dimension 8 and so on and so forth. And these are basically up to some relatively high dimension being classified now by theorists. So 59 is an awful lot to fit at once, so usually you look at some subset, some well-motivated subset. I could look, for instance, at those which affect top physics, of which there's 16, and there was a nice parallel by David Miller from the top fitter collaboration on the effects of these. Right, so the point here is that you have your sensitivity is all coming from distribution and differential information. Right, so this is from top fitter basically, so this is MTT bar, this is the PT of the top, and the standard model here is in red, and if you add in some combination of these operators I showed you on the previous page, suppressed by a scale of 5TeV squared, you sort of see that once you're at large values of MTT, or even not so large values of PT, you start to get these observable differences, right? And so this is exactly why you want to do differential measurements. Hot off the press, there was a paper yesterday by Gauthier-Durieux et al. So I haven't really assimilated this paper, it's 60 pages long, looking at top EFT at the ILC in a click. And the claim is basically that there, if you go sort of to the full 501 TV, you can improve upon HL-LHC results by a factor of order 100. The constraints that you can get. So this is pretty amazing. So along with top quarks, we can also look at a process of particular interest, I think, well, for me, but at this ICHEP has been sort of looking at neutral diboson processes. This gives you constraints on anomalous gauge couplings, anomalous triple gauge couplings. And so here again, pushing towards NLO differential, right? So this is the paper from a few years ago, giving you the cross sections, and then a few weeks, last month basically, Kalbart and Wiesmann had a paper where next leading order, including decays, fully differential for the 4 lepton and 2 lepton 2 neutrino final states. So this hasn't propagated to the experiments yet, obviously, but this is something to look forward to at ICHEP 2020. So these are interesting from a theory perspective, the operators which give you the kind of processes, because they don't enter at dimension 6, they enter at dimension 8 into the effective Lagrangian. So there's kind of 4 of them, 3 of which violate CP, which is also an interesting thing. And usually these have been sort of parameterized in some kind of form factor way. So you have 3 Zs basically, you can imagine. So you sort of have 3 indices on your form factor, but you can translate that into the effective field theory language as well. So this F4 form factor here can be written in terms of the Wilson coefficients that appear in front of these operators. So a question you can then ask is, well, these are interesting, but what are they kind of constraining in terms of UV physics, right? So it's good to think about EFT. It's also interesting to think about more UV kind of models, like what are we constraining when we do these particular measurements. So we wrote a paper on this, and it turns out so did Adam Falkowski and collaborators in the same week. We didn't know we were both doing it, but that's what happened. So you could start, so basically we just sort of thought about sticking stuff inside these loops. You have something like a ZZZ correlation function, what can go inside this loop to generate the ZZZ vertex that will give you then PP to ZZ. So it's been 0, you could have something like a complex 2 Higgs doublet model, complex if you want to get that CP violation. It turns out this gives you really no cross-section whatsoever. And if you match that to the effective field theory, you understand why. It's because these operators, you don't get the D8 operators. These first come in from the 2 Higgs doublet model at dimension 12. So no hope there, really. Spin half, you could add in some vector-like leptons or something like that. Again, you have small cross-sections at the LHC because it doesn't match very well. So, but once you're adding in vector-like leptons, you also have to take these STU constraints into account. You change these polarization functions over here. So this is constraints from STU. And it turns out that this gives you sort of actually reasonable prospects for ILC, for instance, right? So ILC, you can do precision measurements of ZZ, all these green points pass current STU constraints, running up to about 500, 600 GeV, and these can be, these can be constrained at the ILC. Basically, not by the triangle diagrams on the previous page, but by these polarization functions. So this is sort of a higher energy analogy of the STU, Peskin-Takeuchi parameters. Similar ideas have been pursued sort of for Higgs-associated production at ILC by these characters. So it's interesting that you can do this kind of physics at ILC, but not really so well at LHC. And sort of the most recent part of this story to do with neutral diboson production is another paper from last month by Brando Bellizzini and Francesco Riva. So they sort of argue that actually if you want to get these operators in dimension 8, really what you're constraining is something that has spin-2 resonances. So example, KK gravitons, so pretty generic from any extra dimensional model, or pseudo-Goldsteiny. So this sort of means you have a particle, and the particle has some shift symmetry like that. So this would be an exemplar from non-linearly realized supersymmetry, right? So we understand better now from these measurements what kind of theories we're actually constraining and what kind of effects we could expect to find. So as Luis mentioned, there's sort of a few outstanding things that are still to be resolved, right? We haven't sort of finished the story yet at all. PT spectra in particular don't look quite right. Some of that will be, will get better with the electroweak effects. There's also some resummation that probably should be incorporated here up in the tails. I don't know if that fixes things. We sort of have to see, right? As mentioned, there's some small discrepancies in the full top cross-section. There's some small discrepancies in spin correlations. So there's still lots of room for sort of back and forth to improve our overall description of the data. So as more and more data gets accumulated by the experiments, the theory frontier continues to evolve as well. So we now have, for instance, next leading order PT distributions for sort of vector boson production across the board. And this is a lovely image from Gavin Salam, sort of showing in the past, this is from 2016, but it shows you how in the past few years, the sort of snowball accumulation of next leading order calculations. So a lot of the ones here that were appearing 2015, 2016 were next leading order inclusive. So they give you the cross-section, but not the differential information. And so what's been happening since then is there's been a wide number of papers becoming sort of fully differential, which will allow us to get all these, to try and match all of these beautiful experimental curves. So differential distributions is on the menu. Finite mass effects is something that's on your menu, right? So in glue to ZZ, for instance, that's a one-loop leading order. So next leading order is 2 loops, and you really want to get the finite mass effects of the top quark incorporated to describe these things right. Getting all the electroweak in there is right, and then decays and matching. So if you want to get a sort of a picture of the state of the art, yep, I recommend you go to the Les Houches proceedings from this year, which sort of show you where we are in what is known and where we are in what the standard model community and the experimental community have decided what is sort of desired. What is and sort of run a little short on time, but basically you can see that what you want is to match everything with electroweak and decays. And you can do the same thing for vector bosons. You want everything NNLO and with electroweak and decays, and there's similar tables for jets and Higgs. So in the last 5 minutes, I just want to sort of take a tack in a completely different direction, which is machine learning for phenomenology. So we had some really nice sessions. We had a nice plenary yesterday from Elizabeth Sexton Kennedy, and this was also mentioned in the context of neutrino physics. And there were some really nice parallel sessions, and in particular, I enjoyed the sort of the summary talks from Marcus and Stephen. So this is sort of a buzzy kind of an area, and it's being used in a lot of places in the experiments. I want to sort of approach it from the perspective of tagging and resonance tagging, which is more appropriate for this lecture. There's some nice, this has really taken off, and there's some nice reviews available. So sort of the general idea is, one approach that has been pursued, there's a number, is take Atlas, unwrap Atlas. You get an image, basically, when your jet passes through the calorimeter. There's been some large advances in convolutional neural networks to use for image recognition. Exploit those and crank that through some neural network using some GPUs, and hopefully get a better tagger than you had previously. Right, so take your particles, basically, that come inside your calorimeter, pixelize them, rotate them so that the image is now vertical. Right, so this is for W jets, so you're going to expect to find 2 subjets. Put the leading subject in the middle, the next one underneath, reflect it, and possibly zoom in so that all your images look the same. You don't want your network to learn about the symmetries of space-time. We already know about Lorentz invariance. You want your network to sort of learn instead about QCD radiation. Okay. So when you do this, you find images that look like this. So this is an average W boson. This is an average, you sum over a lot of Ws, you sum over a lot of QCD. These things look slightly different, right? So there's a bit more better prongy structure in the W. The QCD radiation is more diffuse. You want your network to be able to recognize those kind of things. So theory, this is basically a hammer. If you give a hammer to theorists, everything becomes a nail. And so this sort of led to an explosion of people writing neural network-based taggers for WZ, Higgs, top, everything you can imagine, basically. In general, these things were outperforming other kind of taggers that people had used before. One trick with this is that if you're using supervised learning, you generally need to train on a known sample. This probably means Monte Carlo. And then you have to worry about, is my network learning about QCD or is it learning about Pythia parameters, which are actually different things. So you can sort of look at then differences between the average jets from different parton showers, right? So Sherpa minus Pythia, Herwig dipole minus Pythia. So you see that these things lead to different amounts of radiation, right, between that central subjet and the second subjet of your W boson. So you end up with different performances when you take this into account. But you could think about, of course, training purely on data if you had a sufficiently pure signal region. There are ideas to train without pure samples, basically. If you had two samples, like a mixed sample and another mixed sample, you could train a network to discriminate between mixed sample 1 and mixed sample 2. And it's been shown that this is actually equivalent with a benchmarking sample to training on samples that are purely signal or purely background. So that's the black and red lines here. They're exactly the same. But the concern, as usual, is these are fancy black boxes. But the more you know, as Ben Nachman says, the less black your boxes will be. So in the last minute, what are we actually trying to learn? I mean, what is the theory perspective on what these things are learning? So one thing you can calculate is sort of a pixel by pixel convolution of the output of your neural network with the intensity of your image, so what your W boson looks like. So that's shown here for two different neural networks. So red is sort of more signal-like, some more W-like. Blue is more QCD-like. So this is telling you the output of what is important to your network, basically, what it's learning. So your network is learning that it's very important, for instance, that you have a hard second subjet here if you want it to be a W boson, and it's anti-correlated with the existence of extra radiation outside that, right? So this is QCD. So it's learning stuff that we already, the things that it's learning we can sort of understand in some way. Right? So another way you can try and understand what it's learning, a question is it improving on what we had before? Is it improving on discriminatory variables like n subjettiness, for instance? So one way you can look at that is look in a really restricted phase space. Get a whole bunch of events which are exactly on the W mass and exactly where the peak of the n subjettiness distribution is. So there's no information contained in these anymore. So if your network is outperforming other variables, it has to be learning something else. And then again, you can look at these kind of, in this restricted phase space, you can look at these radiation patterns and see what is your network learning. So this is for tau 2-1, so the ratio of these n subjettiness variables. So that's exactly here on the pink peak where everything is very prongy, like it has two prongs, so it's like a W. And you see that there's important information in here in the red, so this is signal-like. This is because the W is it's a QCD singlet, so it's going to radiate only in between the quark and the or the Q and the Q prime, basically. So all this QCD radiation in here is sort of telling you something looks like a W. If you have a quark, for instance, that splits into a pair of quarks, it's a color octet, so you're going to get more radiation outside, and this is anti-correlated with the existence so this is more background-like here in the blue, basically. So there's a lot of information that these networks are exploiting, no worries, in terms of sort of radiation patterns, which we don't seem to be capturing in variables like n subjettiness. And so what that's sort of pushing the theory community now is to think about what, one perspective is I don't care what it's learning, I just want the best tagger in the world. And that's fine, but as a theorist, I also want to think, well, what can we actually learn from this? Is this telling us something about QCD that we haven't picked up on before? And so that's sort of now starting to feed back into the theory community and sort of the jet substructure community. Boost is next week, by the way. You'll see probably a lot of talks on this kind of stuff. So there's been some work by Larkowski and Data. Can I use machine learning, for instance, to construct a basis of functions which are ideal for probing the phase space based on machine learning considerations? Right? Can I use machine learning to help me design new tagging functions that I didn't have before? Can I rethink what a jet is? Usually a jet is sort of a tree-like structure, a QCD jet of particles that come together. What if I think of it using natural language processing? Yeah, this is the last one, it's okay. using natural language processing, if I think of the four momenta in my jet as words, and then the clustering history of my jet as a kind of a sentence, like, does that help me in any way? What does that mean? And then there's some interesting work in progress, which is a talk but no paper yet, sort of reimagining clustering from the bottom up in a sense. Think of jets as grass rather than trees. Can you machine learning algorithm not just learn what is W versus QCD, can it learn the ideal jet clustering metric directly from the data? Right? So by a metric, normally we talk about KT versus anti-KT, different kind of jets. These are all differing in the kind of clustering metric for when I put particles together. Can I learn a metric, an optimal metric for distinguishing W from QCD from data? And what does that teach us about QCD? Okay, so I'm originally kind of a BSN person, so really all I want for Christmas is actually a Chargino. But that's like asking for a pony, right? And what we know from our bitter childhood experience is you rarely get the pony. But you need to have a good sort of second thing that you really, really want, because if you don't have that, then you're going to get socks for a jumper. So the second thing I really, really want is an extensive precision measurements program. That's like the race car. And I'm feeling pretty good about getting the race car. And I think that'll be an awful lot of fun, right? So I hope that the picture I've given you is that precision hadron collider physics requires precision predictions, but that's really sort of where we're heading. We get fundamental measurements not only from the standard model, but for searches for new physics, right? So this is where we were 20 years ago with the top mass distribution. This is D0. This is like 4 events per 5 GeV, right? These are 5 GeV bins. These are 20 GeV bins. So it's like 4 events in each 20 GeV. This is Atlas from sort of recently. It's 1,000 events in 1 GeV bin. This is 20 inverse femtobarns. So at the next iChip, when I'm sitting back, sipping on my Staropramen, I look forward to seeing sort of something like this, but with 5 or 7 times more the luminosity, but also all these incredible precision predictions. So in 2 years' time, we'll be sort of 5 times this. But in 20 years' time, so the same distance that we are currently from this D0 prediction, we'll be over 100 times this luminosity. And I really look forward to seeing what we can learn, not just from the standard model, but for BSN from these kind of distributions. Thanks very much.
Thank you, Dr. Dolan, for your extensive theory description. We have time for one question.
Regarding the machine learning techniques, I've discussed one of the papers that you show several plots with many colleagues, and my feeling is that because I was super excited about it, but my feeling is that the more they have worked with jet substructure, the more they are skeptical to the details that you learn of jet substructure that are maybe related to the Monte Carlo generator that you have used and the change between, I don't know, Ervig and Pythia. Is there a way to take into account the systematic difference in the generation of the shower that is not the naive assumption that you run on different generators and you see the difference?
I mean, you can think of it as a theory uncertainty, I guess, right? I mean, the same, I've said that we get, there are uncertainties if you train your net, if you're training directly on Monte Carlo, there's going to be some uncertainties, right? But we also know actually from jet substructure measurements, that even without doing machine learning, there are still these theory uncertainties, right? Like the data is usually sort of sandwiched happily somewhere in between Pythia and Herwig. So I think the thing is not that it's terrible that we have this, it's kind of concerning, and maybe you'd like to train on data if you can. But you just want to quantify the uncertainties in the same way that you quantify theory uncertainties when you're doing like normal jet substructure measurements.
Okay, so just see the differences between.
Yeah, I mean, you could view it. Another way you could view it is a way to improve our modeling and try and think about it like that.
Okay, thanks.
Okay. So thanks, Dr. Dolan again. Now it's a pleasure to call Dr. Sarah Strandberg, which tell us all about the recent result on SUSY searches.
Thank you. So, although I won't be able to put a pony under the Christmas tree, I'll try to spend the next 25 minutes to give you a summary of where we stand in terms of supersymmetry searches at the LHC on behalf of the Atlas, CMS, and LHC collaborations. So there's by no means a coincidence that SUSY is one of the most thoroughly studied extensions of the standard model. It can not only provide a dark matter candidate, but it can also unify the forces at high energy and solve the Higgs fine-tuning problem. So there are clearly a lot of things that are super about supersymmetry. In fact, some people go as far as claiming that the only problem with supersymmetry is that we haven't found it yet. But as I'll show you in this talk, there are still many places where SUSY can hide, and it's our job at the LHC to keep searching. And therefore, we have a broad program to ensure that we get the most out of the LHC data. And as you can see from this plot over here from CMS, we're actually getting a lot of data. So the LHC has been performing remarkably well in the last few years and is continuing to do so in 2018. Most of the results that I'll show you today will be with the 36 inverse femtobarn of 2015 and 2016 data. And in fact, there is only going to be one result with the 80 inverse femtobarns that you get by adding also the 2017 data. So as I said, the main task of the SUSY search program at the LHC is really to find SUSY if it is within our reach. And therefore, we have a huge set of scenarios and final states that we cover, everything from strong production of squarks and gluinos down to electroweak production of charginos, neutralinos, and leptons. We cover both R-parity conserved and R-parity violating scenarios, both with promptly decaying SUSY particles and long-lived ones. And as you can see from this plot over here, the production cross-section for SUSY particles spans several orders of magnitude, with the highest cross-sections corresponding to the strong production of gluinos and squarks, and with the electroweak processes, of course, corresponding to lower cross-sections. As you can see from this dashed line here, if we use the 80 inverse femtobarns that we currently have at hand, we're actually starting to get sensitivity well beyond 2 TeV for both squarks and gluinos. So the search program for SUSY at the LHC is generally driven by simplified models, and you have an example of such a simplified model down here. In these simplified models, we generally put the masses of non-relevant SUSY particles to very high values and assume 100% branching ratio to a single final state. So in this particular simplified model, the stop in this case is assumed to decay 100% of the time to a top quark and the lightest supersymmetric particle, the LSP, which in this case is assumed to be the lightest neutralino. And with these simplified models, we optimize our searches, but we also use them to set model-dependent limits on the masses of various SUSY particles. It's of course important when you use simplified models to make sure that they cover as much as possible of the possible SUSY parameter space. And in order to make sure that this is the case, we actually take the searches that have been optimized on these simplified models and run them through large PMSSM scans, for instance. And because in the PMSSM, as you can see an example of down here, the mass spectra can be considerably more complex, and therefore you can have competing decays and also longer decay chains. And if we find in these large scans that there are regions of parameter space that we're not targeting well with the current searches, then we go back and create new simplified models that are targeting these scenarios. And with an iterative process like this, we're trying to ensure that we're not leaving any uncovered signatures behind. So in addition to these model-dependent limits, we also put out model-independent upper limits, and we also always provide the acceptance and efficiency numbers of our searches in HEP data, for instance, so that theorists can always use our data and reinterpret it in their favorite model. So, of course, in a talk like this, I cannot cover everything. What I will try to do is to give you a general overview of where we stand in each topic, and then I'll focus on the new results. So I encourage you to look at these links below to get a more complete picture of the LHC SUSY search program. And I also encourage you to look at the many nice and detailed SUSY talks that were presented in the parallel sessions, and which I list for your convenience here on the next slide. With that, I will dive into the search program, and I start with searches for squarks and gluinos. So these, as I said, have the largest cross-sections, and therefore, if SUSY exists, they might be the particles that we find first at the LHC. To give you a feeling for what we're searching for, here I put a Feynman diagram for squark production, where in this case, the squark decays to a quark and the LSP. The quarks will give you jets in the detector. The LSP will leave the detector without depositing any energy, so it will give rise to missing transverse momentum, which is called either PT miss or ET miss, depending on which experiment you talk to. If you look at the gluino production Feynman diagrams, the simplest ones, you can see that the final states are very similar. But here you can have also bottom quarks and top quarks, which can give you then B jets and also, in some cases, leptons in the final state. So if we look at the summary of where we stand in this sector of SUSY, you can see that we actually are placing limits on the gluino mass all the way up to about 2 TeV, and squark masses up to about 1.5 TeV. But you have to remember that these limits are really only valid in the most favorable models, and there are many places where the limits are much weaker than this, and I'll show you some examples in the following slides. Just to highlight what I mean, I put here a summary plot from Atlas when it comes to gluino production. And you can see here the limits in the two-dimensional plane of the gluino mass on the x-axis and the neutralino mass on the y-axis. And you can see that these limits here, they correspond to the 2 TeV limits that we were talking about on the previous slide. They are valid for low neutralino masses. So everything within these contours are excluded, but you can see that if you move up in neutralino mass, these limits are actually getting weaker. So in addition to pushing the limits up this way by analyzing more data and getting sensitive to lower cross-sections, we actually also try to make sure that we are covering as much as possible of this heavy neutralino scenarios. So looking at this plot, you can actually get the feeling, of course, from this yellow curve that we are already covering this high neutralino mass region very well. But here you have to pay attention to the details, because this yellow curve is actually corresponding to a different kind of simplified model, where the neutralino is the next to lightest supersymmetric particle and where the LSP is a light gravitino. So here, of course, the gravitino can get large missing transverse momentum, even if the neutralino is heavy. And that's the reason why you have sensitivity there. So this particular NLSP neutralino model has actually just been analyzed in a new result from CMS, where they look at final states with a photon, a lepton, and large missing ET. And here they bin the data in the PT of the photon, the missing ET, and the HT, which is essentially the sum of the energies of the jets in the event, to get sensitivity to supersymmetric models. And in this particular analysis, CMS excludes gluinos up to about 1.7 TeV and squarks up to about 1.4 TeV. Another analysis that is targeting these scenarios with higher neutralino masses, and also where you can see that actually now you have additional SUSY particles between the gluino and the LSP, is this analysis from Atlas that is looking at events with opposite sign dilepton pairs in the same flavor and missing ET. So here you have production of a neutralino 2, for instance, that will decay to the neutralino 1 by emitting either a real or virtual Z boson, where the decay can also happen via leptons. If what is emitted here is a real Z boson, then you expect to see a peak at the Z invariant mass in the dilepton invariant mass spectrum, as you can see from this dashed line here. If the decay happens via off-shell Zs or leptons, you don't get the Z invariant mass peak, but you can still get a nice separation between the signal and the expected signal and the background in this MLL distribution. Also, this analysis makes use of soft leptons all the way down to 7 GeV of PT to increase the sensitivity to compressed scenarios where you have small mass differences between the neutralino and the gluino. And this analysis is particularly interesting because here there was an excess in run 1, which actually is not confirmed now with this larger run 2 data set. So here you can see an example of limits, in this case in the lepton-mediated case, where you can see that you place limits all the way up to a gluino mass of about 1.3 TeV, down to mass differences between the gluino and the neutralino all the way to a little bit above 10 GeV. Another similar analysis from Atlas that is targeting kind of the same processes, but where you instead have tau leptons in the final state, is the search from Atlas that targets both the cases where the neutralino is the LSP and where the gravitino is the LSP. And here, this analysis put limits as high as 2 TeV on the gluino mass for the neutralino LSP case. With that, I move on to searches for spotums and stops, so third-generation squarks. And this is important to look for since light stops is one thing that is needed for SUSY in order to solve the fine-tuning problem of the Higgs mass. And in addition, since the top quark is very heavy, you'll get a large mixing that will generally pull down the mass of the lightest stop so that it can be one of the lighter supersymmetric particles. Starting with spotum production, you can see here that if you produce spotums, they will decay generally to bottom quark and the LSP, giving you B jets and missing ET. In the case of top production, it's pretty similar, but in the top decay, you also get a W. So here you can, in addition to B jets and missing ET, also get jets and leptons. And again, if we try to summarize the limits here, you can see that the limits on stops and bottoms from Atlas and CMS reach 2, or in some cases even beyond 1 TeV in the most favorable scenarios. But again, just as the case for gluino production, the limits depend quite a lot on the choices of the masses of other SUSY particles. So here I exemplify this by looking at the bottom exclusions from CMS and the stop exclusions from CMS. And you can again see that the limits are weakened as you go up in neutralino mass. In the case of stop production, it's even a bit more complicated, because here in the stop decay you have heavy particles, tops and Ws. And actually, if you start to decrease the mass difference between the stop and the LSP, you can get into a regime where the top is no longer produced on shell, and if you decrease the mass splitting even more, even the W can become off shell. And you need dedicated search techniques to find these different decay scenarios. And the most complicated case is this very compressed scenario where both the W and the top are off shell, and you get this 4-body decay to standard module particles. And these are generally also very soft. So there is, in run 2, or in run 1, there was a kind of weak coverage of this diagonal region, and there was a big push in run 2 to really try to improve the sensitivity here. And I'll show you an example of an analysis in this compressed 4-body scenario on the next slide from CMS. But before I go there, I also want to point out that in these particular Feynman diagrams, you can see that you assume that the stop decays to the LSP, but there is actually many models where there are several electroweak Hino states that are lighter than the stop. In particular, here you can see an example from Atlas where you assume that the LSP is a Bino-Higgsino mix, and you get 4 of these states at the bottom of the SUSY mass spectrum. And in these cases, the limits are actually considerably weaker than what you see up here. So here you can see that in the case where the stop is the partner of the right-handed top quark, you can see that the limits are as weak as 600 GeV on the stop mass. So here I come to this analysis from CMS and the compressed scenarios. So here, of course, the decay products in this 4-body decay are going to be quite soft. So here CMS requires the presence of an ISR jet with rather high momentum in order to boost the system and recover some of the missing ET. And in addition, of course, making use of soft leptons, here CMS goes down as low as 3.5 GeV on the muon PT and 5 GeV on the electron PT. And you can see from this plot up here that actually for the various SUSY models, which are these red lines, the lepton PT is very low, whereas for the background processes W and TT bar, you can see that the leptons are much harder. So there's a nice discrimination in the lepton PT. CMS uses a BDT for this analysis, and here you can see a nice discrimination between the background shape and the signal shape of the BDT. And with this analysis, CMS managed to place limits up to about 600 GeV on the stop mass for mass differences between the stop and the neutralino all the way down to 10 GeV. So this is a really impressive result in this difficult diagonal region, but nevertheless, the 600 GeV is much weaker than the 1 TeV limits on the stop mass that we were discussing before. With that, I move on to electroweak searches, and even though these have much lower cross-sections, as I discussed in the beginning, this can still be very relevant to search for in the cases where squarks and gluinos are too heavy to be produced at the LHC. And in the electroweak sector, we generally search both for neutralino and chargino production and lepton production, either directly or in the decays of neutralinos and charginos. And here, the limits depend quite a lot on which scenario you are targeting, so it's hard to give you a ballpark number, but you can see that it's only in a few cases that the limits here exceed 1 TeV. One particularly interesting scenario maybe that I would like to highlight a bit is the cases where the Higgsinos are light. And this is actually something that is expected in natural SUSY, since the masses of these Higgsinos are controlled by mu. And if the LSP is purely a Higgsino, then you actually expect to have these 3 chargino and neutralino states at the bottom of the SUSY mass spectrum with a very small mass splitting in between them. It can be as low as 100 MeV. So when you have the decay, for instance, from the neutralino 2 down to the neutralino 1, the decay products will be very soft. And this is therefore a very challenging state experimentally. So I highlight what we do here with the search from Atlas, where you can see that you either can search for final states with very soft leptons, or if the mass splitting is really small, you can actually have this chargino that decays to the LSP by emitting a really soft pion that cannot be reconstructed in the detector. So what happens here, the signature is going to be a track from this chargino that suddenly disappears when the decay to the neutralino happens. And with these kinds of searches, we're actually for the first time able to probe territory here that is beyond the LEP limit. So here you can see that around a mass splitting between the chargino and the neutralino of a few GeV, these soft leptons are starting to get sensitivity, while this disappearing tracks analysis is closing this plane from below. And there are currently a lot of thought going into how to even further improve the sensitivity in this difficult but important scenarios. So if you allow this mass difference between the heavier charginos and neutralinos and the LSP to be a bit higher, then you can have sensitivity in this kind of search from Atlas, where you search for chargino and neutralino production in final states with 2 or 3 leptons. So it's essentially the same Feynman diagrams as you saw on the previous slide, except here the W now decays leptonically, which which can give you 3 leptons. Again, these are, if we're targeting small mass differences, we again make use of this ISR selection in order to boost the system. And here, Atlas has defined several signal regions depending on if you're targeting these scenarios with a low mass difference or these scenarios with a higher mass difference. And here, actually, for the first time in this talk, I'm going to be able to show you some tantalizing, at least, excesses. So here, in all the regions that are covering this low mass and ISR part of the spectrum, Atlas sees a slight excess. The largest one is this one in the 3-lepton ISR selection, and the excess here is 3 sigma. So this is, of course, not enough of an excess to be overly excited about, but it's certainly something that we're keeping an eye on and where we're looking forward to analyze more data. So another new search in the chargino-neutralino sector is this search for exotic Higgs decay and ZH production. So here you produce a Higgs and a Z boson, and then the Higgs will decay to SUSY particles and by emitting photons. So the analysis is done in a 1 or 2 photon final state. Here, the background is mainly reduced by exploiting missing ET cuts and also variables that are exploiting the balance between the Z part of the event and this photon plus missing ET part of the event. And you can see here at the bottom nice discrimination between the expected signal and the background and the missing ET distribution. So here, Atlas goes ahead and sets limits on the ratio to the standard model cross-section times the branching ratio to photons. And for the case of a massless LSP, the limits are about 11%, whereas for models with a massive LSP and an LSP, the limits are about 18%. So the last topic I want to cover in the electroweak sector is this new analysis from CMS looking for STAU production. It's a new combination of leptonic and hadronic decay modes of the STAU. And it looks both for direct STAU production and STAU production via decays of charginos and neutralinos. And these are important models to look for, since the STAU, just with the same reason as I was talking about for the top, actually can be one of the lightest leptons because of the large tau mass that gives you a large mixing. In addition, models with light STAUs can actually give you the right amount of dark matter via STAU neutralino coannihilation. This is a difficult final state, of course, with taus, and therefore we're not really yet at the sensitivity we need to start being sensitive to supersymmetry models. You can see that in the most favorable scenario in this CMS analysis, which is the one where the STAU is entirely the partner of the left-handed tau, the limits are currently at 1.26 times the expected SUSY cross-section. So with that, I move on to searches for RPV SUSY and long-lived particles. And I would like to stress that it's very important for us to also search for R parity violating SUSY, because the constraints that we normally put on R parity conservation are actually stronger than the ones that are needed from proton decay, where only B minus L is needed to be conserved. So there are actually quite a few viable RPV scenarios that we for sure need to search for. Here, of course, the lightest supersymmetric particle is not going to be stable. It will decay. And therefore, you don't get the general large missing ET signatures that you can use in other SUSY searches. So you need to exploit other techniques in order to separate the signal from the background. And here is a really nice cartoon from CMS showing the diversity of these long-lived particle and RPV searches that I won't have time to go into in this talk, unfortunately. But one thing I want to point out is, if you have RPV SUSY and if the couplings are weak, then you can actually get long lifetimes of the SUSY particles. And long lifetimes is also something that can arise in R parity conserved SUSY. For instance, if the decays are happening via very virtual particles, such as in split SUSY, or if the mass spectra are very compressed. So in this RPV and long-lived particle regime, the limits are actually often quite strong, and you can see that they can even go above 2 TeV, as is the case for this metastable gluino search from Atlas. But again, it depends quite a lot on which scenario you are looking for. I would like to highlight a bit the diversity of this long-lived particle and RPV area by showing you a reinterpretation search from Atlas, where you take the standard R-parity conserved searches and R-parity violating searches and reinterpret them in some different sets of models. So one model that is looked at is R-parity conserved SUSY models, where you actually have a variable R-hadron lifetime. And to remind you, an R-hadron is a particle then that consists of a gluino and quarks or gluons. And if the gluino is long-lived, then of course this R-hadron can also have a lifetime. So here in this plot, you see the limits on the gluino mass in this reinterpretation search as a function of the lifetime of these R-hadrons. And you can see that for prompt decay, so low lifetimes, the standard R-parity conserving analysis are the most sensitive. And as you go up in lifetime, you have these specialized analyses starting to kick in. For instance, the ones that are searching for displaced vertices, or here an analysis that is searching for the characteristic energy loss in the pixel detector from these R-hadrons. So another set of models that are used in this reinterpretation are R-parity violating SUSY models, where you actually change the strength of the RPV coupling. So here an example of limits on the stop mass as a function of the strength of this lambda double prime 323 RPV coupling, which then will make the stop decay to a bottom quark and a strange quark. And here again, you can see that the limits on the stop mass cover a really nice and wide range of coupling strength values, but you can also see that when you transition from one type of analysis to the other, you have these kind of weaker spots where the stop is actually allowed to be as light as 600 GeV. Another nice RPV search from CMS is this new one searching for resonant production of SMUons that are both produced and are decaying via this RPV coupling lambda prime 211 that couples the SMUon to the up and down quarks. And here, one of the discriminating variables is this Slepton invariant mass, which is constructed from the 2 muons and the jets. And you can see that for the signal models, it peaks nicely at the expected value. And here, CMS sets limits on the cross-section, here shown in the plane of the SMUon mass and the neutralino mass. The last thing I want to cover, of course, is the very nice program to search for SUSY from the LHCb experiment. And I want to highlight one of their new results where they search for a scalar resonance that decays to a pair of muons. And these are important for SUSY since these light scalars can appear, for instance, in the next to minimal supersymmetric model. Because of the very good mass resolution of the LHCb experiment, they can actually go very close and search around this epsilon resonance between 5.5 and 15 GeV. And in the zoomed in picture here, you can see the data that is following nicely these epsilon resonance shapes. And then you have various SUSY signals here in color. And since the data follows quite nicely the prediction without the signal, they go ahead and set limits. And these limits are in agreement with the CMS limits in the regions where they overlap, but you can see that because of the nice mass resolution of LHCb, they can actually go much closer to this epsilon resonance and exclude some additional parameter space. Of course, there are much more SUSY relevant searches from LHCb. For instance, they search for long-lived particles, both decaying semi-electronically and to jets, and they, of course, have a very rich indirect search program for SUSY. With that, I come to my summary. So I've shown you that we have a lot of new results at 13 TeV that are being produced at a steady pace. We're currently working on completing the search program with a 36 inverse femtobarn data set, and we start to see the first results with the 80 inverse femtobarn data set. Even though we have a vast and versatile search program for SUSY at the LHC, there is no evidence for SUSY yet, and this really sends a strong message from the LHC on what type of SUSY that can be realized in nature. In the most favorable scenarios, I've shown you that we actually have quite strong limits on the SUSY particle masses, but I've also shown you that in the more challenging scenarios, the limits can actually be considerably weaker. So there is still quite a lot of SUSY parameter space that is still not so well covered, and the next step is to complete the search program with the entire run-2 data set, which is expected to be about 150 inverse femtobarns. And with that data set, we really have to ensure that we cover all the signatures that are within our reach. Thank you.
Thank you, Dr. Strandberg. The floor is open for questions.
Very nice talk, Sarah. So for this dimuon resonance search from the previous slide, so I was a little bit puzzled that limits actually by CMS and LHCb are so closed. It's not Atlas CMS where you have similar experimental conditions. Luminosities are quite different. There are many other. So is it just occasional coincidence or is there something deeper here?
That's a good question. So of course, LHCb has a better mass resolution. I mean, that's why they can go closer, but on the other hand, they have a smaller acceptance, right? So maybe these two things interplay, but I'm not entirely sure since I'm from neither of the experiments, but yeah.
I didn't see too much about the more non-traditional type of model. I mean, everything was, I mean, given that you're not seeing very much, is there any effort, maybe in parallel of doing something with some of the more generalizations of SUSY, for example?
Yeah, absolutely. So that's a very good point. And this is a bit what I alluded to here in the last slide. Of course, since there is no sign for SUSY at the LHC yet, we really have to make sure that we are covering, you know, all the final states that we could possibly have sensitivity for. And that, of course, includes also looking at, you know, more non-minimal scenarios, maybe with slightly more expanded sectors and so on. So this is for sure something that there's a lot of work going into at the moment to try to expand the search program beyond, you know, the kind of vanilla SUSY to make sure that everything that can be covered is covered with the upcoming data set, yes.
As I don't see any other hands, thanks Professor Strandberg again. And now we have the last talk of the morning, Dr. Daniele Del Re, who has a daunting task of covering all of the exotic.
Good morning, everybody. It's a pleasure to show the exotics results to this conference. So let me first give you some description of what exotic analysis means in at LHC. So there are many unanswered questions from the standard model. For instance, why there are only 3 families of leptons and quarks? Why only 4 fundamental interaction and not 1? Why only 5% of matter is made of standard model particles? And why the most massive particle of the standard model is only 200 times heavier than the proton? Clearly, there are many more of this, but the goal here is really to answer to these questions. And by doing this, we would like to cover all the possible signatures to look for the unexpected. And in doing this, we would like to be as model independent as possible. And clearly, we are going to use a specific model to test the analysis and also to interpret it. But the real goal here is to try to explore without putting any possible constraint in the searches. We want to look for extremely high masses and really go for exotic, for instance, look for new quarks, new leptons, but also new unconventional signature. I will go into that later. We would like also to find a candidate for dark matter. And in particular, in doing this, since we really want to go also for the unexplored, we want to exploit new analysis technique to boost the discovery potential. There are hundreds of results, and unfortunately, I cannot go through them. I will just stress, I would like to give you the full picture and stress the most recent, some of the most recent results in this land. So the luminosity used for this analysis, similar to the previous talks, are based mainly on 2016 statistics, because in general, these analyses are complicated, are not trivial, and then you need a bit of time to understand your detector. And for some of those, we are going to use also, we have used also 2017 statistics. So a total of 80 inverse femtobarns. So LHC clearly is a unique playground for this kind of researchers. First of all, because you have objects with huge energies. You have an example on the left plot over here, where you have an event display for DiJet event, the largest mass DiJet event recorded so far, around 8 TeV invariant mass, which is huge. But we have also something like more unconventional signatures. Here you see an event display from Atlas, where you have a single jet and nothing else, if you like, on the other side of the detector, which could be a sign of new physics, for instance, dark matter, which is traveling through the detector without leaving any signal. Clearly, if you want to do this kind of analysis, you need a full understanding of your detector, because if you see nothing, you want to be sure that you are seeing nothing because your detector is working properly, not because of inefficiencies, for instance. I will discuss about resonances, which are the most uncontroversial, if you like, a striking signature of new physics, because you have small systematics related to those. I mean, the usual picture is something like this. This is dielectron actually distribution from Atlas. You see that you expect from your background a smooth distribution, and your new physics stuff should show up as peaks at the tail of the distribution if you're concentrating at high masses. Clearly, you can look at two-body resonances, and you can combine several different objects. And when I said that we are trying to do it very broadly, we are really using all these different kinds of bodies, if you like. The simple ones, like photon, electron, muons, but also the most complicated ones, like TOPS, or Ws in hadronic decay channels, which are complicated to be reconstructed. Then clearly, we're also addressing specific issues. Like, for instance, we would like to explain the light mass of the neutrinos, looking at, for instance, at seesaw model, type 3 seesaw models, where at the very end, this will end up having new fermions decaying into, at the very end, leptons and neutrinos, for instance. Then you have a striking signature in your detector of leptons and missing ET. Then also, we would like to see why the number of the generation of lepton and quarks is the same. I will discuss this later, looking at leptoquarks. And then, for instance, also to address the issue of having tree generation and hierarchy in mass of fermions. And in doing this, we look also for excited quarks and leptons, which are giving also a striking signature of the detector, like an electron, muon, and a photon, also a quark and a photon, or a quark and a gluon. Then, another kind of analysis we are doing in CMS is related to long-lived and unconventional signatures. Actually, you can have many different scenarios where you have long-lived. This is the simple formula of the width of the process. And you see that if you have small couplings, or amplitude-suppressed process, or phase-space suppressed process, you are going to have a small width and then a long life of the particle. And clearly, if you are in this regime, you can have many different signatures in your detector. You can have a displaced vertex, for instance, which is appearing at a certain point of the tracking detector, for instance. You can have a displaced photons, for instance, which is not pointing to the primary vertex. You can have a disappearing track. This has been described also before by Sarah, where you have a track with a certain point decays in something which is not reconstructable, brought by some new physics particle. And you can have a stable particle, which is heavier than the muon, for instance, which is traveling through all the detector. Clearly, the idea is to exploit and to look for all these signatures and to search for new physics in those. Another kind of analysis we're trying to do is the search for dark matter. If we produce dark matter, this is the diagram of dark matter production at LHC, we are going to have dark matter in pairs. And clearly, if there's nothing else in the detector, you're going to see nothing. And you need a trick to trigger and to reconstruct those events. And then you look for ISR events, where together with this, you have also the production of a high energy object, which could be a jet or a photon. By doing this, then at the very end, you're able to trigger and to reconstruct the missing energy related to the dark matter particle. And then this becomes the key variable to look for new physics. So let's start from the physics results, and let's start from resonances. at the moment, there are very striking limits. This is an example of the Dijet distribution from CMS. As I mentioned before, I mean, you can go up to 8 TeV in invariant mass. And clearly, this reflects the fact that you can put, depending on the model, also limit on the lower limit on the mass. For instance, the order of 8 TeV, 6, 8 TeV, depending on the model. You can see by yourself that nothing is showing up. But the same can be done for different final states, for instance, Z prime or W prime decaying to leptons. And also in this case, the limits are very strong. What I would like to stress here that now that we have increased the center of mass energy with respect to round 1, I mean, this was the limit for a W prime for round 1, around 3 TeV. Then after changing the center of mass energy, there was a big change. And after that, the limit in mass is increasing as expected, as a square root of the luminosity, which is good, but clearly you don't have to expect a big jump in the future. I mean, you're going to improve these limits here, 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 but after that, you cannot do much better than this. So that's the reason why, for this kind of searches, we're also exploring more complicated regions at low masses, where, I mean, the experimental, let's go back. Like the experimental part, the experimental part is easier, if you like, in this region over here, because if you have a peak, it would be simple to be distinguished. While if you go in this region over here, it's more complicated because you have to put down to the backgrounds. And this is what we are doing in different analyses. For instance, for the Dijet, here what we do is we look at the different mass region. For instance, here is the case between 500 GeV and 2 TeV, which is a region, in principle, if you do nothing, prohibited from the triggers. You cannot trigger a Dijet event, storing the full event in such region. But what we do here, we just save a reduced event at trigger level, basically the kinematics of the jets, and then we can perform this analysis. Again, there's no sign of new physics here, but clearly this is important to cover also this region of the phase space. If we go even lower in mass, and we are talking about here below 150, we exploit another trick. We look for ISR jets produced actually resonances produced together with an ISR jet, which is a good way to trigger on those. But the drawback is the fact that if you have this kind of topology, then the resonance is produced with a boost, and the jets are merging each other, and you have to have a hoc method to reconstruct the invariant mass of the two jets. This distribution you get at the end. You see the peak of the W and the Z, and you can look for additional peaks due to new physics around in this region over here. And still, there is no sign of new physics. The fact that we are covering a large phase space is shown by this plot, which is comparing Atlas and CMS for this kind of searches. And you can see that between 50 to several 50 GeV to several TeVs, we are able to cover, I mean, the phase space everywhere. And what is also interesting from this plot is the fact that now LHC is really doing better than any other experiment, even at low masses, which was not the case before. And you can expect by increasing the statistics that this limit in the cross-section will go down, 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 while here is more difficult because of the issue of the high mass resonance search I was discussing before. Clearly, if you want to explore the low mass region, you can do something fancier, if you like. I mean, suppose that together with the resonance, you produce something else, right? And you're not seeing the resonance just because you are sticking to the hypothesis of having just the resonance alone in the event. But if the resonance, for instance, is produced together with a lepton, then you can put an additional constraint. You can trigger the event looking at the lepton in the event, and you can again redo the same analysis of Dijet. And clearly, you can go down to much lower masses. Another thing we do is we tag on the final state of Dijet, for instance, looking for B jets. And again, this allows you to push down the trigger thresholds and to explore lower regions of the phase of the mass and then the larger regions of the phase space. And what you can also do is to look for wide resonances, which is particularly important for dark matter interpretation, because if the resonance is wide, the coupling is large, and then clearly you can explore a wider region of the phase space by doing this. always talking about resonances. This has been discussed also in the theory talk by Matthew. What you can do is to look for final resonances going to bosons. Okay? If you have a high mass resonance which goes to boson, the boson is low mass compared to TeV resonance, and then it's very boosted. Then what you're going to have is that the decay of the resonance, for instance, in two quarks here, is going to be boosted, and the two quarks are going to merge each other. Actually, the two jets are merging each other. You construct the resonance as a single jet. We do it in several different channels. This is an example of a resonance going to a boson, a vector boson and a Higgs decaying in BB bar, and the vector boson is reconstructed in leptonic mode. And you see by yourself that the limits, but this is true also for other cases, single analysis, are of the order of 3-4 TeV. This was a result from CMS. In Atlas, clearly the research program in this line is very similar. This is an example for a fully hadronic decay of a resonance into V bosons, and actually also Higgs bosons, where basically is a fully hadronic event. You can see from this plot, this has been shown also by Tancredi yesterday. It's clear that, this was the previous limit from Atlas, and this is the new limit from Atlas, and this was what you get just by scaling the luminosity, okay? This tells you that you can do much better than just the scaling of the luminosity by improving your analysis technique, in particular low masses. And this is what has been done in this case by having a more detailed reconstruction of these substructures of the jet coming from a V boson. And on the right, you see a combination of many different channels where these two are combined in modes with hadronic modes, leptonic modes, and you put everything together in a model where basically this new resonance is described with the couplings to Higgs, to fermions, as it happens for instance, for the Higgs, and in a coherent way, you can combine all the channels, and you can see by yourself that in specific regions of these couplings, the limits are of the order of 5 TeV in mass for the new resonance. This has been shown from Matthew before. I don't want to go into the detail of this. So again, if you want to exploit analysis techniques for this kind of searches, you can do it at the extreme by using, for instance, deep learning. What I would like to stress here is that the experiments are already trying to implement this, and clearly this is an example where you are able to distinguish between the different substructures from Higgs boson, V boson, top quark, and backgrounds, and you can use deep learning to distinguish between among the different hypotheses. Okay, new quarks, new leptons. You see here that one of the most interesting things and anomalies in particle physics now is these anomalies in the BD case, both in this ratio, this start on nu, DL nu, and the new universality K mu KE, which are not turning out to be as expected. And this can be due to the fact that together with these diagrams over here, you can have leptoquarks, so particles which are also decaying in leptons and quarks, and they can contribute to this kind of final states. Then, if you put this together, you're going to change your amplitudes for these processes. This is true in this case, but also in the penguin diagram here on the right. That's why it's very important to look for this kind of resonances, which and their signature is very striking. This is an example of the production of these leptoquarks in pairs, where you have at the end a leptoquark decaying is a first generation leptoquark, so it's decaying in electron and jet. Then at the end you have an event 2 electrons, 2 jets. And clearly, since you don't have any missing ET, the signal is striking. You expect a peak here in the invariant mass of the electron and a jet, which is not, unfortunately, it's not happening. And after looking at this, you can put limits on the mass of the leptoquark, which at the moment are of the order of 1.4 TeV. You can do the same kind of technique, again, leptoquarks in pairs, this time for 3rd generation. And in this case, you have the leptoquark decaying in top mu, for instance, and in tau b. So the idea is the same as before. In this case, it's more complicated because since you have tops and taus, there is some missing ET involved because of the presence of the neutrinos. But again, I mean, you're able to reconstruct the invariant mass of the lepton quark, and you can put limit, which again are of the order of 1.4 TeV. This is another analysis which is looking for something different. The vector-like quarks, which are basically counterparts of the top and the bottom quarks, which are decaying, you can see this from this diagram, which are decaying to W Higgs and Z bosons to a quark, a heavy quark, B and top. And if you produce them in pairs, at the very end you have a very complicated final state, which can be reconstructed in many different ways. You can imagine that you have a plethora of final states here, and they can be combined. At the very end, you have a degree of freedom which is related to the fact that this resonance, new resonance, can decay, this new quark can decay in different modes involving W, Higgs, and Z. You have 3 modes, if you like. And then you can build a sort of triangle, and the limits, depending on where you are in the triangle, in mass will be different. This is the combination of all these modes, and you can see also in this case that depending on where you are in on the plane, you have limits of the order 1.3, 1.4 TeV. Just to give you the feeling, we have many, many searches in Atlas and CMS, which I cannot go through. I mean, you have an equivalent plot. This is for Atlas, equivalent plot also for CMS, but just to let you know that it's much more than what I'm showing here. We are really covering the full phase space of signature and energies. Long-lived. So this has been also introduced by Sarah before. In LHC, we are looking at these unconventional signatures, which require, in general, a very deep understanding of the detector. And these are 2 examples of LHCb and Atlas, where you try to map the material of your detector. Because, for instance, if you look at a displaced vertex, clearly that can be confused with a simple conversion. And the conversion depends on the material. And if you want to perform this analysis, you have to have a super accurate description of your detector. An example is a disappearing track analysis. I mean, the idea here is you look for a new particle which is traveling through the detector. At a certain point, it decays to a neutral particle. So this is the case of chargino and neutralino, and a soft pion. None of these 2 can be reconstructed. Then you're going to see some hits in your tracker and nothing else in the outer layers of the tracker and the calorimeters. Here you see the resulting limits you have for this kind of analysis. In this case, the limits are reported as mass as a function of lifetime. And all this region here is excluded. What you can notice here, you have 2 main constraints here. The first one over here is basically limited by your granularity or resolution of the detector. While on the upper side of this plot, you are limited by the size of the detector. Because, for instance, if this particle travels outside the tracker or outside the calorimeter, you're not able anymore to distinguish or to see it. And clearly, what you're going to see is for a lifetime, which corresponds to a few meters, which is order of 10 picoseconds, 10 nanoseconds, you're starting to be less efficient for this analysis. The acceptance will go down. And that's why you have this sort of shape for these searches. This is a different analysis. Instead of seeing something which is disappearing, we want to see something which is appearing, so-called emerging jets. This is in a scenario where you have dark QCD, which gives you possible candidates for dark matter. And basically, you have a pair of this new heavy mediator, which are then decaying in 2 quarks, actually, a standard model quark and a dark quark. The dark quark then hadronizes and produces dark pions, which are particles with a lifetime different from 0. They can travel. And then basically what you're going to see is a jet like this, because the hadronization of this dark quark will produce a dark, if you like, a dark jet, where you have many pions inside, which are just appearing at a certain point in the detector. And because of this, you're going to distinguish from the usual jets from the standard model by looking at particles, tracks inside the jet which are not pointing to the primary vertex, or they have some hits missing in them. And then by doing this, you can again put limits on the mass of these mediators as a function of the lifetime of these dark pions. Clearly, again, you have this shape I was describing before, which is connected to the detector and the acceptance. This is the analysis shown also by Sharam yesterday, dark photon search at the LCB. Here, the idea is to look for dark photon, which is produced via this kinetic term, which depends on this parameter epsilon. So epsilon is basically the cross-section. And in doing this, you just look for the dimuons invariant mass, and you look for this distribution in a wide range of masses, you see, between MeV range until several GeV range. This is the mass of the Z and the W, just to give you the scale. Clearly, you can do this with prompt photon, but in some cases, if the epsilon is so small, the particle can even become long-lived. And if you look at displaced vertices, you can even do the same analysis for much lower values of epsilon if you are sensitive to that. And this is what the LHCb is doing. And you can have a limit like this where you have this epsilon parameter as a function of the mass of the dark photon. What you have at the end is a limit like this, which is showing you, this is the blue region here, that we are, in LHCb, the results are already comparable to the previous experiments with the region which is only done at the LHCb. And what is also interesting to see here is that there is some sensitivity for long-lived, for the long-lived case, and there is some exclusion there as well. Clearly, if you were going to add more statistics and you improve your detector and the trigger, you can extend these 2D limits much more, and you see what's going to happen at the end of run 3. So it's very intriguing and appealing to see what's going on with this analysis in the next years. This is just to tell you that also at Atlas and CMS, similar searches are done for dark photon, actually dark forces. The difference here is that the kinetic term is between the Higgs and the dark Higgs, or between the Z and the dark Z. But at the very end, you're going to see something similar, which is dimuon final state, which can be either pointing or actually prompt or displaced. And you can have limits also in terms of epsilon as a function of the mass, in this case, of the dark Z. So the last topic I'm going to describe is the dark matter search at the LHC. I already said before that the way to see dark matter at the LHC is to look for initial state radiation mainly, where this kind of thing can be a gluon, a photon, a Higgs, or a V boson. Clearly, you can have many different analyses. The striking, the most relevant point is really the reconstruction and the background modeling in the missing energy distribution, because the real point is that background and signal look very similar to each other. And if you want to perform this analysis, you have to understand very well the distribution to see this tiny excess over here because of dark matter. And the main backgrounds in this case are due to, for instance, for the monojet analysis, are due, for instance, to standard model events where you have a jet which is recalling to a Z, and the Z decays to neutrinos, for instance. And this is a signature which is identical, and this is an unreducible background, to the dark matter one. And so that's why, all the care is put on understanding the background. And this is quite remarkable. This is the ratio data Monte Carlo in the missing ET distribution, that the uncertainty on this ratio, so if you like the understanding of your backgrounds, is of the order of a couple of percent at low missing ET and 10% even in this region over here, which is a remarkable results for this kind of analysis. It's not trivial at all. This is obtained by looking at different control samples, combining things, and also with theory effort to reduce the systematics. At the very end, the limits you get from this analysis is a limit like this. We are using a simplified model, which we have basically 4 parameters, which are the couplings of the mediator with the quarks and the dark matter, and the mass of the mediator and the mass of the dark matter. Then you extract a limit like this, where you exclude this region over here of mediator versus dark matter. And you can see the results for the different ISRs. So this is monojet, monophoton, mono V boson. And clearly there is a region where you can't be accessed because of the fact that you have off-shell mediator. This region over here cannot be accessed by this kind of method. And what we do to access also that region is making this consideration that if you have this diagram of here, which is the simplified model I was describing before, if this new boson, this new mediator is coupling with the standard model, you have a GQ, then you can have also, let's say, both in production and in decay. So if you are in this regime over here of simplified model, this new mediator should decay also to 2 jets. And this is why, I mean, the limits, the analysis I was discussing before for dijet and dilepton can be translated as well in this plane. And clearly, since you have a limit on the mass, you have bands, vertical bands, in this case, which put strong constraints in this plane. And the same, clearly, this depends on the value of the couplings you're assuming. For instance, if you switch...
You should concentrate in getting to an important point.
Yeah, I'm almost done. You can have different couplings. If you go for couplings which allows you the decay in leptons, then you have also the lepton contributing. And this is what you get if you combine these results with the direct searches. The only difference here, instead of having the mass of the mediator, you have the cross-section of dark matter versus proton. You can combine with the direct searches. Okay, this is just to show, I won't go into the detail, that you can do the same searches with spin-zero mediators. In this case, you have also top quarks contributing, as expected. And I mean, you can have limits also in this case into the plots. To conclude, we have a coherent rich program of exotic searches at ZSC. We have several different signatures, as I described before, so a very complete program to look for new physics. There is no sign of new physics yet, unfortunately. We expect some improvement, which is moderate at high masses, but we're almost mostly concentrating in the intermediate region of mass or on new analysis technique, as I hope I showed you before. The conclusion is that there is still plenty of room to search for new physics, and we hope that next year we would have some new discovery in this lab. Thank you.
Questions? Yes.
Ilya Garbunov. If it is possible, can I have 2 questions? So the first one is that you can during this conference, you can constantly hear an idea that people are kind of tired of new limits. First of all, well, mostly because it's just the most simple models we explored so far. And we have to move more to some precision kind of studies to search for new physics. Can you think of some relatively small set of variables or decay modes which can be suitable for that kind of searches? And the second question is, you also can hear from theorists that the problem of dark matter and dark energy probably can be solved without introducing new particles. And can you think by just some fine-tuning of standard model, let's say, can you think of the ways to check those cases?
Okay, as far as the first question is concerned, it seems that I completely failed my goal of showing that this is not the end of the story for new searches in this kind of physics. So it's clear, at least this is my point of view, this is not the end of the story for this kind of searches, because I mean, it's true that at high masses is difficult to improve, but it's also clear that if by adding statistics you can reduce your cross-section, you can expand your phase space. So according to me, we don't have to go, there's still plenty of space to do these searches in this area, together with clearly the fact that you can do also precision measurement. I mean, so according to me, I mean, it's not true that we are tired of doing this kind of physics. And this was the goal of my talk. The other question is, clearly, I mean, this physics is relying on the fact that the dark matter is produced at LHC. So clearly we are relying on that. I know that there could be other explanations explanations on dark matter which are not expecting new particles, but clearly it is not the topic of LHC, unless I didn't understand your question.
Okay, as we are running a little bit late, I think we can close this session. I would like to thank all of the speakers for very professional presentations. And we should reconvene at 11:35 after the coffee break.
Thank you.